Good afternoon, or good morning, or good evening, depending on where you're watching us from. This is day 3 of the WeAreDevelopers Mobility Days, and I say welcome. So, before we start this whole program, let's have a look at the agenda, which is brought to you by kind sponsorship of Volkswagen. So, we will soon start to see Vasily, who will talk about artificial intelligence for autonomous driving. And I'm sure that my colleague also wants to show you the agenda screen. Thank you. Because I do not know the agenda by heart, so no chance. After Vasily, who will talk about how to prepare training data and validate sensor inputs, we will have a look together with Sergey, who will analyze people in mobility in indoor locations like hypermarkets or malls. And then also have a look together with Stefan on augmented intelligence for transport planning. To say in detail, he will have a look at the human-in-the-loop modeling. And then at 4:30 we will talk with Svetlin, who will show us how to debug machine learning code, and whoever did it knows, I hope he brings tricks. And at the end of the day we will close everything off together with the team Dosana, Olivia and Jose, who will show us how to build a food delivery app using location intelligence and matrix routing. So throughout the whole day you will be able to use this thing here over there. It's Slido if you are on wearedevelopers.com/live. If you are on YouTube and you want to join in, you can also go to slido.com and use hashtag WeAreDevsLive. Just try it out once. We have a little, it's not a guessing game. It's just we want to know what was your first computer. As you can see, there are some brands which seem to be a little bit bigger. The smaller things are also very old, kind of interesting stuff. C64. It's another age. So that being said, use this to ask your questions. At the end of every session, the questions will get answered. So before we continue and really start this program, there is one more thing I need you to know, and it's that this event falls under the code of conduct of WeAreDevelopers. The short version is: please be respectful and treat each other nicely. And the long version is this one. So that wasn't too bad, I think, and also not too hard. And now, without putting any further blockers between you and the agenda, let's head over to the stage and say hi, Vasily. How are you? Okay, you're welcome.
Hi everyone again. So maybe I will start from the very beginning maybe. So this is the talk, and I hope the sound works fine now. This is the talk entitled AI for Autonomous Driving Outside the Car, Training Data Preparation and Sense Validation. I'm Vasily Baranov. I'm a team lead at the company Sim Automotive, GmbH, which is a part of Luxoft, of the company called Luxoft. And this talk is based on several projects that we did in Sim Automotive and in Luxoft, but it's also not, the projects were not done only by my team. It was a collaborative effort of many teams. So I just represent this effort of the results of this work, the projects, but of course that our team also did a certain portion of these projects. We'll go quickly through the table of contents again. I will start with the introduction, talk a little bit about deep learning and about the use case, why we need artificial intelligence outside the car. Then talk about artificial intelligence outside the car, the two use cases that we have. This talk is not very technically deep, so seasoned deep learning or machine learning developers in the field of autonomous driving may feel themselves not very challenged, but hopefully still interesting for the listeners. And thanks for inviting me again. I'm happy to present this at this venue. Hope you enjoy the talk. So let's start with deep learning. So what we need from an algorithm, especially in the field of computer vision, is that we supply raw data to an algorithm. Then we apply this algorithm, which is sometimes called inference. And then the algorithm produces labels or detected objects, for example, in an image, detected cars, detected pedestrians, bicycles, etc. These tasks are often solved these days with the help of deep learning. You can think of deep learning as of matrix multiplication, many steps of matrix multiplication with some nonlinearity. So let's say here, for example, an image of 100 by 100 pixels can be represented by a column or a vector of 10,000 values, or actually, since we have 3 channels, red, green, and blue, by 30,000 values. And then an algorithm or a deep learning algorithm multiplies big matrices of 30,000 by 30,000, at least to the first step, to this column, to this vector. Then you repeat this precision many times, and then you get as an output another column or another vector, a set of numbers, which bear some meaning which you assign to them. For example, it's positions of cars or pedestrians in an image, and the encoding which box is a car, which box is a pedestrian. And all the parameters in these matrices are trainable, so you have to fine-tune them. Of course, there are a lot of tricks and secrets of the trade, how to optimize it, and about the structure of these matrices and so on. But at the heart, it's something like this. So you need to fine-tune all these parameters, which is called training. So you need to train an algorithm. And how do you do this? At first, you take an untrained algorithm where all these numbers inside the matrices are random. Then you provide training data to this algorithm. So raw images plus labels. For example, images where all the cars are labeled and all the pedestrians, etc., etc. Then the algorithm or the deep learning algorithm or framework fine-tunes all these parameters, and you get a training algorithm that can solve the task that you wanted to solve. So this algorithm will obtain raw data as an input. Then when it is applied, so in the inference step, it produces something useful to you. Now let's talk about use cases. So why do we need, or why we might need artificial intelligence outside the car? The first use case in general, let's actually at first talk about why we need label data for certain tasks in autonomous driving. annotated data. So images plus cars, bicycles, pedestrians marked in them. The first task, a big task, is validation. So we have, let's say we have a computer vision pipeline that runs inside the car with a dedicated set of sensors, and we want to check how well it works. So then we run this pipeline that runs inside the car over a certain set of images, these images, and then we compare the results of this pipeline with the ground truth or annotated data. Another big use case is training itself. So we need to train this algorithm that runs inside the car, and we provide a set of raw data, images, and a set of label data with bikes, cars, pedestrians labeled there to this algorithm, and then it's trained. There are, of course, many more use cases. For example, usually people work with intelligent content management systems for data in this area, autonomous driving. For example, you would like to automatically mark your data as being obtained or gathered in summer or winter, or that the picture was taken in daytime or at nighttime, or whether the weather is sunny or rainy, whether the picture was taken at a crossroads or a street. And then you can intelligently select different scenarios out of your database of scenarios for different tasks. And another part of this puzzle is sensors and different types of annotations. The typical sensors that are present in cars that are dealing with autonomous driving, it's of course cameras that take RGB data, the LiDARs, which gather point clouds with laser beams, and the radars, which also gather point clouds, but slightly differently looking. There are different types of annotations for all these data streams. And in both 2D and 3D data, like in pictures or in point clouds that look like this, you can annotate bounding boxes, 2D boxes that surround the objects, that enclose the objects in them, so in 2D and in 3D. You can annotate key points, so probably you can't see it, but for example, joints of people or other crucial parts of cars, for example, vehicles, and you can annotate scenes semantically. And here you have pixel by pixel annotation, where, for example, all the red pixels belong to vehicles in this example, in the middle example. Or you can have instance-based semantics annotation, where you say that you mark polygons or silhouettes of objects, object by object, so different objects have different silhouettes. This is also something that computer vision pipelines at certain steps shall produce that run inside cars. And let's talk to the problem statement or to the problem explanation. So here is a personalized example with Semi. So please meet Semi. And Semi, or we, want to validate sensors and train algorithms for autonomous driving. For this, we need data. So we need, our Semi recorded a lot of data with different sensor streams that we discussed. And now we need to annotate this data in the ways that I presented. But there is a problem that usually it's too much data to annotate manually. So different ways of annotation may require different time per image or per frame. But for example, semantic annotation may require up to 45 minutes per frame, or also LiDAR annotation can be quite complicated. And for 1 million frames, you need 375 man-years. And data sets typically used in this computer vision area grow over time exponentially, which is depicted in this fancy plot. There are even more problems with this scaling, so you need to organize people and resources. You need to implement data maintenance and quality control, and you need a lot of engineering effort. You need some managers for data streams, data engineers. You need to collect data. You need logistics and route planning, etc., etc. Then there is at least one of the solutions to this problem is automation. So there are two sorts of source of automation. It's or automated labeling is semi-automated annotation and fully automated annotation. With semi-automated annotation, the humans work together with some algorithms that assist manual labeling or annotation of these frames. So, for example, with the help of computer systems of automatic assistance, humans can relatively quickly label the figure that is on the left of the image and in a way that is shown to the right. Another way is to employ fully automated annotation, when an algorithm runs completely independently and produces the automated picture to the right from the original raw data to the left. Here, you don't need any manual efforts at the stage of annotation, but there is an increased technical effort on the side of algorithms, hardware, orchestration, etc., etc. And of course, you can switch, or along the project or along the timeline, you can switch from completely manual annotation to semi-automatic annotation and then to fully automatic annotation by reducing manual effort for labeling or annotating all this raw data that you gather for this use case that I talked about for validation and training algorithms inside the car. So here, once again, are these use cases in a nutshell. For validation and training, you take raw images, then either with the help of semi-automatic annotation or fully automatic annotation, you get labeled data. And then you can use this labeled data for these two use cases, either for validation, so that you validate the computer vision pipeline that runs inside the car, or for training, where you train the algorithms that run inside the car. And at this stage, you might wonder what's the difference is if here we have algorithms that run inside the car, and at this stage, to the left, I hope you can see my mouse actually. Maybe I'll turn on the highlighting, spotlighting. Yeah, this stage. So what's the difference between these two algorithms? And the difference is in the fact that when you run the algorithms outside the car, you have much more freedom. So inside the car, usually the devices are not so powerful and they have real-time constraints. Obviously, when the car is driving, you would like to react quickly. You have constraints on GPU memory, on random access memory, etc., etc. And outside the car, you can utilize many powerful GPUs. You don't have time constraints for processing. You don't have GPU memory constraints, random access memory constraints. And also, you can go back and forth in time inside your recorded sequence, which is often a big advantage. So just a moment. This slide is not. Okay. Of course, this problem is slightly more complicated because often you need a certain step called retraining, also for your custom algorithms that are used for automation. After quality control, if it turns out that something is not working perfectly, human annotators can correct certain discrepancies, and you can retrain your algorithms according to this corrected data. So this was the problem introduction and to the use cases. And now I would like to go to present these two use cases that we were working on. The first use case is validating algorithms that run inside the car, as well as sensors. So basically, again, the project was dealing with validating a sensor, or actually a LiDAR sensor that was installed on a car. And we would like to, and also a computer vision pipeline that was used with it or delivered with it. And we wanted to, the project was to develop a system for validating it, to validate this LiDAR sensor. And on the algorithmic side, this is how you can represent validating, or the idea of validating 3D bounding box detection. So a computer vision pipeline inside the car would produce certain 3D bounding boxes around objects. In this case, they are cyan bounding boxes. And another algorithm would, a ground truth sort of algorithm would produce this pink or purple boxes, which are supposed to have slightly better quality. And then you can compare these two boxes and determine how well the algorithm inside the car performs. So this is a little bit about the system setup. As I told you, we were validating, the project was about validating a LiDAR sensor. And to do this, reference sensors were also installed on test cars, in particular 12 cameras with high resolution, 1 front LiDAR and 4 360-degree sliders. All these sensors were actually producing a lot of information, 3 gigabytes per second, and the project was aimed at collecting 23 petabytes of data in total. There were a lot of hardware installed in the car: data loggers, RAID capacitors, switches, sensor synchronization, etc. And there was a lot of hardware used for deep learning. Here is basically, now in the presentation, I will just present some videos with the results of automated data annotation. So I hope you will be able, they will be transmitted correctly. So this is the result of the algorithm that detects 3D bounding boxes inside the point cloud. And this algorithm that was developed inside Sim Automotive, it can detect traffic signs and also classifies them by their type and track them. So different traffic signs are tracked and numbered. We'll go quicker through it. With this algorithm, you could then detect, it's another typical algorithm where you can detect bounding boxes around vehicles or objects in 2D images and runs segmentation inside these objects, as well as classify them into trucks and cars. Another important use case for algorithms, which is actually not directly used for training or validation, but is relevant due to GDPR guidelines, is anonymization. So with this algorithm, we detect blur license plates as well as faces, so that they can be forwarded to labelers, to humans, but with protected identity. So these algorithms were used in this project then to also the algorithm that worked in 2D. They were used to detect 3D boxes and 3D objects, and then these objects were compared to the results of the computer vision pipeline from the car. And of course, it's just the algorithmic side of the project, but there are, as I mentioned, a lot of challenges in data management. And for this reason, we actually, or Sim Automotive, developed a platform for data management and algorithm management, so that can take, which is called C-Data, that can take care of data acquisition, manual labeling, automatic labeling, processing, and analytics. So we're integrating our algorithms there. Of course, this is a big this was a big endeavor, this platform, and a lot of technologies are used there, which I do not cover and do not intend to cover. So it's just an overview of the technological level of complications that arise. I will skip this slide to save some time, and I will switch to another use case, how deep learning can be used for assistance during data preparation. So for semi-automatic annotation, basically. This is the second use case that's for algorithms. Manual annotation of cars, pedestrians, or bicycles happens in special tools. And one tool was an example of such tool is C-Label, which was developed at Seymour Automotive, which is part of Luxoft now. Here you can see the bounding boxes around cars and polygons around cars. And you can assist human labelers, human annotators that prepare labeling data manually with certain algorithms that run inside tools. And this video will demonstrate how this happens. So for this algorithm, the labelers could, or annotators could mark a 2D bounding box around an object, in this particular case around a car, then click a special button or a shortcut, and then the algorithm would detect a polygon around the car. So here the box is marked, the car is selected, and then the button is clicked, and the polygon is marked around the car automatically. And in this video, the same thing happens with this pedestrian. The challenge for this algorithm was that it shall run in real time, but also on CPUs, so no GPU assistance, so that it can run on normal PCs, which are used for with this tool to do manual or semi-automatic annotation. And for this was done. This particular task was done in our team. We did certain optimizations of neural networks. So it's a deep learning algorithm that heavily optimized for CPUs that runs sufficiently well in real time. And it's a single network that runs for different object types. So this is the final results. And obviously it can save a lot of time for tasks that require labeling of polygons in 2D, which in tasks that are related to sensor fusion is anyway, can still be relevant for detecting 3D objects if you do sensor fusion. So if you fuse 3D and 2D modalities, so to say. And basically that's it. Thank you so much for your attention, and thanks organizers for inviting me and for giving this opportunity. And I'll be happy to answer any questions if we still have time.
Hi, Vasily. Can you hear me? Obviously not. Hi, Vasily.
Hi, Vasily. Can you hear me?
Yes, hi.
Yes. Okay.
Sorry
Sorry for the inconvenience with the audio. We're still fighting behind the scenes and using some backup equipment. I have some questions from the audience for you. And the first one is, how much data cleaning do you need to do?
In principle, in this particular, so we didn't do much data cleaning. I know that in typical machine learning projects that deal with tabular data, you usually have to do a lot of data cleaning because you have columns with different, for example, value types with money or with text columns, and then or with hours, and then sometimes you have commas as decimal digit separators, sometimes dots, sometimes you have euro sign after the number, sometimes not, sometimes there are typos if it's tabular data. So for typical or for non-computer vision, maybe machine learning tasks, data cleaning is very essential and can take a lot of effort, but in our case, actually, we didn't have to do a lot of data cleaning per se, because here you have images and then you have labeled data. But what was important, or what is often or always important, is aligning on formats, because every company or every supplier or every customer, they expect slightly different formats for labels. You have to mark 2D boxes in this way with 4 corners, or maybe with center and box width and box height. And where is box width, where is box height? With polygons, either how exactly you mark the polygons, etc., etc., etc. Also the same for 3D. How do you encode 3D boxes? How do you encode rotation matrices, whether it's quaternions, whether it's rotation matrices, in which frame of reference everything is, and so on and so forth. So this is something that usually takes time, alignment on the data format. And also, we actually were spending some time in this project on calibration, resolving the calibration formats, how the calibration between different cameras was written down, how was it encoded. It costed certain effort, and the calibration itself actually also costed certain effort.
Okay.
Yeah. Maybe one last remark to this question. In these types of projects, it seems that it's also very important to get at least the first possible data as soon as possible, so that you can see the data as soon as possible, and first to maybe think at once which algorithm you would choose, or how you would tweak the algorithm, and which direction you shall go, which sensor fusion you might need, which constraints on the data there are, where the sensors are located. For example, if LiDAR is located at the top of the car or at the bottom of the car, you will see very different pictures, and it might have certain implications.
Okay. So second question goes, I think, kind of in a similar direction. How much impact does the fact that you have enormous data lakes? Okay, that doesn't seem. Does the fact that you have enormous data lakes have? Okay. Do you need that every time, or is this for a base model only?
Here I'm not quite sure what is meant exactly. So we created this base model, or the first model at first, and then we were constantly improving it, given additional data that was incoming, and then that was corrected inside the retraining loop after our fully automatic to semi-automatic implementation.
Okay.
And then when the project, it of course depends on the duration of the project. If the test data is incoming, then you would be running your algorithm for a certain period of time, not only for at once, one time.
Okay. Next question is, what is your opinion?
Sorry, now I can't hear you.
Oh, okay.
Try it here again. What is your opinion on a game engine, Unity 3D, or similar usage to generate and label the scenes for teaching a neural network?
So in this project that I was talking about, we didn't use this, but it's a big industry, and there are a lot of companies that do this, and sometimes it's of course important to enhance your data, or to enrich your data with simulated frames in cases when you can't gather a particular type of data, especially at the beginning of the project, when you, for example, you need data in winter, and it's probably easier to simulate it. And there are, of course, many companies that do this, develop their own engines, not only Unity. There are companies that try to map certain areas of cities with to build high definition 3D maps of cities where you see all the asphalt patches on the road, which are usually not so trivial to simulate. And then with this high quality reconstructed data, you can then switch between day and night, for example, or introduce some more pedestrians or some more traffic in the streets that are almost real streets. So it's definitely a big industry as far as, or sub-industry as far as I know in this area.
So from what I hear between the lines, there is still a difference between using a game engine and using a dedicated simulation, or?
Yes, so I have to be honest, I don't have that much experience in this area, but I'm pretty sure there is, because as I told, so we investigated at least this problem, and there are companies that are focused specifically on very detailed reconstruction of a scene, not only what a game engine can produce, that try to mimic all these tiny details that you can't maybe even think about, whether a guardrail is broken or whether you have some random stone falling away from your pavements, something like this.
Yeah.
It's definitely different.
Oh, so there is plenty of room for science, I guess. Endless field. So thank you. And I'm very sorry for all the audio problems. There were seems to be equipment failure. Let's have a look that it doesn't continue like this. Yeah. Thank you, Vasily. And to the audience, we will be back soon with Sergey. And
see you later. Bye. So, hello, dear audience. Welcome back in a place with audio and with Sergey. And he will now show us how we find out how we move in hypermarkets or malls. Yeah. Hi, Sergey.
Hello, Stefan. And I guess I should start.
Yes. See you
Okay.
later.
Yeah.
Bye.
Hello, guys. This time the presentation is slightly different. It's again about the mobility, but it's a really, interesting case about people mobility and how we can track that information, especially for hypermarkets or malls. It will be a kind of a technical diving into different technologies which we use for the last 6 years with some comments, positives and negatives, and also yeah, and let's see how it goes. So first, let's start with me. That's yeah, Sergey. I'm one of the founders of Data Science Society. Something like management experience. I started as a developer, analyst. I work with data. Then I start on the management path. I have graduated in Vienna Academy, Executive Academy in 2014. And after that, I decided to start working with different projects. And we call it startups. One of them is Tiki, which is a mobile ticketing platform for transport. So yeah, I was in San Francisco, in London. Also, we have some customers, and at that time I also started Data Science Society. The main driver and the main idea was behind to be a place where people dealing with this exotic domain data science to have a platform where they can share, experiment, and learn. And ShopUp is a company which we started 6 years ago, which is again a focus, as you can imagine, with data and how data science and AI can improve the life of retailers and e-commerce. Probably why retailers and e-commerce. So we made a lot of interviews and we identified that it's very easy to get data from retailers and from the e-commerce. And about the case, about the main problem and the scope which I want to discuss here is we all know people. People who are walking, no matter is it in the malls, no matter is it in the store, the hypermarkets, but it's so hard to have that information, what they are doing, what is their patterns, and also to make some judgment around it. So the situation is that in indoor, the GPS is not working. The GPS as a technology, the mobile stuff, our phone with the GPS. So we need to use different alternatives. And here, as a representation of the human, of the person, we can focus on its way. On its pictures, on this how that person looks like, and make analysis on the top of it, and make certain sensors, certain technologies which can capture the person itself. Also, we can use and the fingerprint of the mobile. We all know that the mobile is, the day we buy a mobile phone, we want to be connected. So being connected means that it transmits data. And I will show you later on. And the third part is if you use a kind of something external, which you can enforce the person or the audience or the visitors to carry with them. So it can be like shopping baskets, shopping carts, or something similar in that direction. It can be like a pass, like a car, like a pass for a store or for something else, or within indoor enterprise, let's say that way. So in order to, let's start in look into the phones. I really like to make that comparison that phones are like nails. Like nails, they want to be strong. They want uh, to broadcast. I mean, just to show their charm. So they're active. So no matter is it a 3G, Wi-Fi, or Bluetooth, the phone is the active. So it says, "I'm here. Is there someone who I can speak to?" Here we have 3G and 4G signals which are transmitted in different frequency. We also have Wi-Fi, which we have in 2.4 gigahertz and 5, and the Bluetooth. The Bluetooth is very similar to in the range as a Wi-Fi, and also you can imagine as the signals behavior. So about the 3G and 4G signals, 6 years ago, we decided to explore that option and see can we intercept of this mobile phone when it connects to 3G or 4G, some identification and identify where that phone is and what is it doing. So here what we find out, there are such receivers. Their cost was around 1,300 to 1,400 to 500 USD dollars. Something and also something what we find out that the data which transmitted is encrypted, which is, yeah, it's logical. So we were not surprised about that. And then about the user ID or the ID of the mobile phone. So we can take the package, we can intercept the packages, but the user ID, it always changes. And also about the localization and path tracking, there were some difficulties to achieve this, to achieve the localization. And something else which we work on that was yeah, we noticed that at that time one of the networks in Bulgaria, because I didn't mention that at the time I'm from Bulgaria, was not with encrypted data. Now everything is okay, but at that time there wasn't such. And sooner or later our hesitation about is it legal or not. And also we noticed that it is this product needs to be used with mobile operators, which are tough clients. And at the end we decided that we will not dig into 3G and 4G because the customer is different and the tasks which we want to be solved are completely different. So then we decided, okay, let's see how the next one, which is the Wi-Fi. The Wi-Fi, how it works, each phone being switched on with its Wi-Fi, it starts transmits data. And if you have router on which is on such mode, it's a monitor mode, or I mean, some people call it sniffing. It's a normal monitor mode where you can gather all information transferred from the routers, and this can be easily done. What it means easily? OpenVRT is a Linux-based operation system which covers around 95% of all type of routers. There are already done packages. So we also developed one router, one small router, which is something like this with a battery inside, 4 or 5 hours, and it is easy to be done. Also, such big companies like Cisco, Mesh, they also provided such monitoring mode, which can be configured very easily. About the data which we gather for each mobile phone is, as you can see, the RSSI, it's a received signal strength. It's indication between 0 and -100. Also the MAC address, which is the identification of the phone, the SSID, which is the string of the network which we log in. Also, sometimes it sends MAC address of the SSID router. And also there are other service data like packages and other stuffs in that direction. About there's something like we decided to dig just to show you what are the main challenges of the signal. Normally, the signal, the RSSI, if it is between 25 up to -16, there is a distance of 1 meter. But then after that, the distance starts grow exponentially. So we see that around -70, it goes to 7 meters. If we go here, -80, it goes above 10, and very easily it is supposed to reach up to 100 meters. And here, as you can imagine, this part between 3 to 20 meters have the error rate is very huge. The error rate of converting RSSI to distance is increasing if the RSSI is decreasing, like between -70 to -80. Something interesting here, which also is will show what are some of the challenges, is if we have a 300 number of samples sent. Something which I didn't mention here is that each phone sent bursts. We call them bursts. There are 15 channels, so at a particular time it decided and just make a burst. And that burst these are different packages. So here on this graphic, what it shows that between 75 to 80, around 90 to 95% of the packages get lost. So here's how many packages are received and with a particular strength. So how close it is. So the further it goes, above 5 to 10 meters, we start having losing a lot of packages, a lot of bursts which we can intercept. So something like dependencies. Also, it is very interesting that each mobile phone, each operational system has its differences. For instance, about the frequency, how frequent these bursts are happening. For Android, normally it's very important. Is it in a sleep mode or in an active mode? If it is in a sleep mode, for Android, it's between 1.5 minutes up to 3 minutes. For iOS, it is between 2 or 3 minutes to 5 minutes. And it was interesting at that day, it was 5-6 years ago, BlackBerry was one of the most secured one. I don't know, is there someone who is using it, but just as a reference at that time. Also, at that time, iOS and Android starting changing the MAC addresses. So if my phone is in a sleep mode, no matter that it is this phone, every time it's sent these bursts, they're with a different MAC address. And also it's very interesting that the strength of the signal also fluctuates a lot. And how it fluctuates, for instance, in this mall, we have, it is in Canada, so it is on X around 500 meters and Y around 400 meters. There was a signal once, and for this floor, we have around 50 routers, 50 receivers. And there was one burst, which have been called from all sensors, which was so rare because normally we have 1 to 2 maximum on average. We have two signals to intercept from different routers, and sometimes there are more. But what we have here for the approaches, how we can work with this data, which, as I showed, is very noisy and also sparse. There are different filters which you can do. There's low pass, moving coverage, and or different kind of areas. Also, we started with true iteration. I mean, our first approach was okay, we have 3 signals, draw circles, and see where the intercept is. After that, the next approach is with the Kalman filters. Kalman filters, the concept here is that you add the motion of the phone of the person. So at each position, you are trying to predict, knowing what was his previous and what is his pattern of movement, probably what is his next position at a particular time. And also together with the signals, you try to combine both of them and see where is the highest probability that person can be. So this gives us a lot of good results. Something which we used at the end is a particle filter. Particle filter, we break it down into three different layers. The first one is about signal analysis. Just to show you, these are again, you can see like three circles. So each circle means that router have intercept a particular mobile phone, and based on the circles and on the 3D histogram, we see with the lighter color that where probably that person can be. Also, the next layer, once we have this these squares, we go to add personal motion based on time difference. What it means that we know that let's say the person is moving in a particular direction with the speed of 0.5 to 0.8 meters per second. And also we know that probably 10 seconds before that. So we multiply 10 seconds with the speed, and we also put a kind of here I can show it's like we generate particles which will, I mean, how dense they are. It depends of the direction which it is and the distance. And after all of this, we also put another layer which is with mappings, mapping of the of the store. So if there are some walls here or different places, we can remove all these points. And at the end, we will show, we will, ignoring them, we will have the ones which are really obvious. For instance, here, I don't know, okay, can you see, but this green dot was previous point, and now the predicted is in the yellow one. And here, for each dot at the end, we have not only the position, the coordinates, we also have the direction, the speed, and the possibility, what is the probability of being there. And using this particle filter also is a very good approach, especially if you have if you have only two or one routers who get that information, because you can put the direction, and only based on one circle you can try to predict where that person is. Something like comments here, or what is positive or what was negative about this approach for tracking people is, first of all, the positive part is it's passive. I mean, no one is needed to install something, to carry something with them. The only need is to have switch on Wi-Fi. Also, the good part is that you can gather repeating customers, so the customers who are coming frequently. And something else which we noticed, that combining this technology with counters, like video counters at the front, or with combination of different counters at each venue, you can give a very accurate information about the number of people, and also about probably what they are, how they are moving. Something which the negative sides here, yeah, to be honest, signals, there is a absorption, reflection, deflection of this signal, which is a big negative. I mean, we are losing a lot of packages. As I mentioned, loss of signal. We are losing if we have more than 10 meters, the signal starts, we are losing as a volume. Also, there are black spots. The disadvantage is that, for instance, in the corners, it's so hard to get the information that someone is there, and also the model doesn't work quite well identifying the corners. Also, we're having problems with the strength of fluctuation. How strong is a signal? It really depends on that, and we don't have a control which operation system of which mobile device changes it. And something else at the end, there were around 20 to 25% of overall traffic. Something else which I didn't write here is that the precision is within 5-10 meters, even more. But the main problem is that sometimes the phone disappears for 5 minutes, 5 to 10 minutes, and even within a mall, you can see each point probably with a distance of more than 100 meters. So this is the negatives. Or if you go further, the next one technology which we decided to explore, and we have different implications, was the Bluetooth. The Bluetooth is a concept is very similar. The frequency is very close to the Wi-Fi. The concept here is that instead of there are two ways. Instead of beacons who transmit particular data, and there is a beacon gateway or receiver, and then it captures the data and transfer it to the server. Also, we can do the same and with the mobile phones if they are switched on, if the Bluetooth is switched on, and we can identify such kind of information. Again, we have monitor mode, which is same as the Wi-Fi, and beacon. Here for the beacons, we implemented it in two different approaches. One of them is for shopping carts, where they want to know is the cart coming closer to a particular area. And something which was interesting for cleaning lady. In several malls in Canada, what we did for each toilet, there is a camera which counts how many people are coming. So, and because the precision is high, after 70 people, there is a SMS sent to the cleaning lady to go and clean it, and we put such kind of beacon into her cleaning basket, so we know at what time the lady goes and how long she stay. Here, I mean, the positive side can be used for small areas. We all know about these main ranges. Somewhere there are 3, somewhere there are 5. But to be honest, I mean, it doesn't work out well if the distance is more than 20 meters. Even, but the good part is that it's low cost and battery lasts over a year. As a negative, yeah, it's similar with the Wi-Fi in terms of signals, in terms of the frequency, in terms of how it behaves. With the, again, for more than 20 meters, we noticed that around 95% of the packages were lost. Also, there is a high cost for big venues, especially if the task is to get precise information where this beacon is. You need to put a lot of receivers, especially if we talk about malls or hypermarkets. And yeah, I mean, the next one which comes naturally, and it comes as we work through, was the video cameras. There was a request to start using video cameras and images and making such analysis of the people movement and their behavior. I will not go in very details here because it's like, I mean, here the positives are really obvious. It's a passive monitoring. The accuracy is about 99%. It's very accurate now. Now there is on the market very good solutions. Also, you don't need to start developing. There are companies who are offering you data as a platform. So you install their devices, and they're providing with the data, the raw format, in a way you wanted to make and start build your models, which really saves you a lot of effort, and it's very easy to be deployed and start implementing. About the negatives here, it's relatively expensive installation, and it's relatively, for instance, for one of our customers, I mean, Kaufland, for their hypermarket, we computed that it's needed around 85 cameras on the ceiling of 6 meters. Also, to install this, it is very expensive because it's above certain limits. There are kind of regulations, security regulations. You need to build a kind of a, building skeleton, which people's will need to work on. There are a lot of wires, a lot of internet, so internet which need to be accessed. So the most expensive one was the installation and the maintenance rather than the hardware itself. And also one of the negatives is that it can't really measure the returning customers. Here we have for one of our customers, so we use a platform. You can see here on the crossing, it will start increasing if they cross the red line. There is what is the height. Now they have with what is the gender. This is a horse crossing. Now you see the horses passing by. It's again one of our customer in Canada. Also, if we go here now, now we can see 3 different areas, zones which can be crossed, and they're counted, but also and the height which is there, and importantly, what is the path. So it takes the path and it still goes without changing who are doing when, what are doing. So it can be done for different heat mapping and different other analysis over that. Here, and something, yeah. So just to sum up, now we did what is on the mobile phone. Next, we make analysis on the physical part of the people who are working there. And something else which come up as a request, it was like 2 years ago for Kaufland, is that they were willing to track with very high precision, with a precision of more than one meter, where and what are the pattern of their customers into the store, which will help them for the merchandising. Also, there was a request not to be dependent on batteries, so battery can last more than almost a year or around a year. Also, it's important to be fast deployed. I mean, easy for maintenance, deployment, and also low cost. Low cost, just to get a understanding for one hypermarket, shopping carts are around 500 to 600, and baskets are again the same or even smaller amount. Something else what they share, that for 1 year, around 20 to 30% of the shopping carts something have happened with them. It can be stolen, it can be repaired, it can be moved from one store to another store. So that's why we need to be sure that if the sensors or devices who are installed there are not going to be very critical. So in order to receive this, to have high precision above 1 meter, I just want to introduce you one of the, inertial measurement unit, which is a combination of gyroscope, magnetometer, and accelerometer. Interesting for you how big can be, these sensors are probably these 3 black holes, and comparing to a battery, how big this can look like. What is the accelerometer? Accelerometer itself, what it does, it's measure non-gravitational acceleration. What it means that it measures the changes of the speed. If something is moving, or if it is stopped and start moving, this acceleration is the changes of speed over a particular time. Here it's how it looks like if it is unstable, and if it starts moving, there is a force, and it's start measuring that data. The accelerometer here, we can see that on X there isn't such kind of change. On Y and Z, it rotates in one direction and then returns back. Something here, what I can share from a development points of view is that you need to be very careful about the metrics here. Who are they? What they mean? We were using Bosch sensors, and it took us a lot of time to understand what are the metrics and how to convert them. Then the gyroscope. The gyroscope is again it uses Earth gravity to help determine orientation. Orientation means there is an angular velocity change over particular x, y, or z. So here the rotation part, this blue one, is what the sensor interpreted, what it captures. So here we can see, I mean, it is 0 to 200, that that person rotate on left, then on right, then again on left, then again on right. But what you see, that the average, it moves, it slips down. So there you can use different techniques. It is the good part is that it is the data is reliable, but because it is velocity, it's a change of something, there is an error which is aggregated, as you can see here, and you need to find a technique how to complement it, how to remove it. And the next one is magnetometer. It's a digital compass which measures magnetic field and changes in the magnetic field. You can see from here it was 270, someone returns left, then returns right, then slightly left or right, and again you can see such kind of changes around 90 to 100 or yeah, based on his position on the earth. About the challenges here, the challenges is that acceleration is a derivative of velocity, and velocity but itself is derivative of position with time. So there is an error which aggregates. Also, something normal which you can receive is if the green line is the path of your movement, then the other one, they changes or flip on another way. Here is one example of me walking in that hypermarket. So you see that the starting point and returning point, which is somewhere here, they didn't gather. Something have happened here. Here is the cashier in that stage. So the solutions which can be used here and can be done is that there are different compensation filters. What it means, compensation filters? It means that, for instance, accelerometer and gyroscope, because they are capturing the changes, so they're very fast. They're very reliable in fast changes. But because they aggregate error, after that error is a problem. But for instance, magnetometer itself, it's like it doesn't work out well for fast changes, but it's stable for a longer term and doesn't have such kind of errors. So there is a different literature about that, but the concept is this about the compensation filters. Also, there is sometimes you can put additional hardwares to clear the error, probably some hears who can say, okay, you are exactly at this position, which can calibrate the whole model. Also, there are different models can be used. Again, we started with Kalman and particle filters. There are also other models can be used. Also, we were thinking to use deep learning, but the problem was how to learn itself. So the only way to learn itself was to put a camera on the wheel, on the shopping wheel, and in that case we can learn the deep learning models. And something else which we did the last 2 years is we created a new product which is called SenseAI. So SenseAI comes from the sensor. So here, SenseAI, how it begins, the project started like 2 years ago. Yeah, you are seeing me because I was supposed to make some of the testing during in March for the coronavirus. To make the testing here on the top, that was yeah, the advantages to be at, during this pandemic part is that being at home, yeah, I have time to focus on one thing and experiment. Yeah, I don't know how that, yeah, that my wife didn't kill me, but at least it was fun. I mean, it was fun to experiment, to have some focus on this. This is, I mean, me with a laptop, and here it's like uh, a big board where you put all the sensors and you are able to experiment and see how it goes. Something which we did, we built, I mean, a lot of models together with the team which we work. I was focused on this one, which is in to identify, because one of the problem is once the shopping cart start moving, where that shopping cart is. So here the red one is the shopping cart, and this dot is where the model predicts that the shopping cart is. As you can see, it takes time, like it is like 3 to 5 minutes to find it here. Okay, there is an error, but at one point the model itself start localizing with a high precision where the shopping cart is. And this is one of the models. The other model which we did was yeah, there are different purposes. It was to track the movement and clear some of the noise. And the third model is it's based on SLAM. The concept is similar, but it's very specific what kind of data you have in order to build a map, to use the movement of cards in order to make precise mapping of the card. And this gives us an opportunity to learn unsupervised in order to get the information where how the maps looks like and where the people are going, because normally it's not only in the store. And to build this map, initially it took like for the person who was doing it, it's like 4 to 5 hours, so it's manual work, and we want also to automate that. And generally, this is the sense AI did what we which we work on. I didn't mention about the company and who we are and what we are doing. We are ShopUp. ShopUp, our main concept and main idea is to help retailers and e-commerce with latest technologies, with latest innovation. We are we have expertise in IoT. We have expertise in AI. We apply a lot of different models. We have AI expertise, retail and e-commerce projects. This is relevant to Sense AI, which I showed to you, and the other one which work with MOS, also for Wi-Fi analytics. And something else which we develop is catering platform, which is customer data platform. The main idea is to help e-commerce website with the data science advancement. But in order to do that, we need to combine different sources of data. So that's why, by the need of making data science, we developed this customer data platform. We have various projects in that domain, from different kind of recommenders. We also work with the structured data, like propensity to buy, lead score, repurchase patterns. We also work with images, I mean, attribute classifications, with audio, with text, with unstructured data. We also have experience with the chatbots, and generally, I think that's it. In terms of customers, we have some customers from US, Canada, England, and many from Bulgaria. And I think that's it. That's it all. If you want to hear, because normally we are very active on LinkedIn, and we share a lot of good knowledge, expertise. So you can find us on our website or on LinkedIn. And I think that's it. Stefan, now it's your turn.
Hello, hello.
Oh yeah.
Very interesting. I'm still trying to find out what I actually want to know from you, but here comes the first question from the audience. And I think somebody has an idea. Can we go and triangulate the position with a multitude of approximate positions so we get a spot of high probability?
Let me just
Yeah. So can we go and triangulate the position with a
yeah,
multitude?
I can read it. Multitude of approximation terms, so we get a spot of high. Yeah. I mean, you can do this. The problem with the data, my feeling is that you are talking about the Wi-Fi stuff. The problem is that we have very rarely received three signals. Normally, is the main challenge is that we use already deployed network of Wi-Fi's, and they are done good in order to have Wi-Fi relatively reliably for a mode, let's say. But here, for us, in order to have precise information, the routers needs to be very close, like up to within the range of 10 meters. And one of the technique is to use this triangulation and have such kind of zones, or it can be particles, whatever you can choose. The problem is with the data and with the real case scenario, because you will have one or two, maximum two or one signals per burst normally. So you need to start solving this problem without three triangulations, and yeah, this is the problem there.
And this is not a question from the list, but once you know the base problem you are tackling is to find out where do people go to and where are they, but how do you take it a step further? Because you know they were in the ale with the pasta, yeah, or let's do it COVID style, they were in the ale with the toilet paper. How do you get that that connects?
Yeah, something what we did, it was very interesting for the Wi-Fi for one of the modes, because they have a mobile app, and when you install your mobile app, you have granted access to your MAC address. And what we did, we provide them, we made a recommender because you know that within one store, within one mall, there are between 100 to 200 stores and even more. And when you are there, I can see what's your preference, in which stores you stay more. Then each store has its labels. I mean, what kind of products, what kind of interest. And what we did is a recommender once you enter, we can put recommendations for particular stores which have promotions. I mean, from our side was having this data as a first layer, and then building recommenders for different tasks. One of them was about advising someone to go in a store because there is a promotion or something like this. Also, something else with the images, with the video camera, you know, it has different implications, especially for the queue. The first, I mean, the most important part which I have seen it at the beginning was at the airport for queues management. And normally they use alert systems. If they see that there are a lot of people going to the queue, in order to trigger to the managers to open additional queues or just to open additional checking stations. So yeah, what I show you, there are different and various tasks. This is the first layer when you digitalize the people movement, and then you can make a recommender even in Kaufland for the cashier. Once they have information how many people are coming, they can predict what's going to be the volume at the cashier. So do they need to open additional cashier desk or such kind of stuff?
How soon will he run out of change?
Yeah. I mean, it was funny. I mean, every time when we speak with them, they're giving different options. Something really interesting was they said, "Can we make for our employees like a soccer players? You have seen soccer players analytics, how much time he have run, score or whatever, such kind of stuff." And they said, "Can we make something similar to know our employees how they perform, what they're doing, but from operation point of view, not from a tracking point of view or this kind of stuff." And it was interesting that every time everyone have different opinions about this, how then the next layer can be used once you have stable localization.
Okay, so that's very interesting. Thank you, Sergey. And I think we will hear a lot of more stories from you in the future.
I hope you enjoyed. Stefan, as I promise you, it's a different domain, but again, working with the IoT and data science. So it's like it was. I hope it was interesting for the audience, and stay in touch.
Yeah. Okay. Bye bye, Sergey.
Bye.
And dear audience, we will be back with Stefan Petrov right after a short break. Bye. So, Stefan is back and he brought Stefan. Yeah, I'm here with Stefan Petrov and he will tell us about augmented intelligence for transport planning. Hi, Stefan.
Hi, Stefan. Yeah, I'm good. It's a beautiful gray day. Yeah. So a perfect day to present something about augmented intelligence for transport planning, I believe. Okay, so my name is Stefan Petrov. I'm head of research at Transmetrics. Transmetrics is a software as a service company aiming to solve problems in logistics. And yeah, we mostly like create a solution which does solve some operational research and statistical estimation problems for the logistic industry. We solve a variety of problems and we do both we both develop our product and create some bespoke solutions and play around with some interesting problems. And I want to tell you a little bit about some of the problems that we see, especially in terms of compliance and how we try to solve them little by little. So this is a bit about us. We do predictive optimization products, for supply chain, predictive capacity planning, asset repositioning, predictive asset maintenance. We've had some good results with some clients. And we have this funding from Horizon 2020, which is for financing completion of product development and completion of our product and expanding the market to mid-size enterprises. So this talk is not about AGI. It's sorry if somebody feels cheated, if you're not interested. So I'm going to be talking about achieving human-ish or superhuman performance, hopefully, certain business tasks, automating certain processes, solving a particular problem under uncertainty. So we have some complex business problem with distributed decision making, a lot of people involved, incomplete data, and we want to somehow improve the operations of certain companies. So it's not about AGI or similar things, but it's about bringing decision support systems that hopefully make sense to our users. So this is what this is going to be about. And so I'm not going to use the words AI or augmented intelligence so much. I'll mostly be talking about statistics and optimization and how to avoid some pitfalls when trying to make expert users use them. Yeah. So I'll start with discrete variables. We have combinatorial optimization, continuous variables, continuous optimization, and how is the internet? Sorry, yeah, well, it says it's unstable. Okay, basically that's just a very basic thing. And in a sort of project for creating a new analytical solution, one normally understands the business process, gathers the requirements, then does some model formulation, data collection, optimizes some objective function, then presents the results, and then gives the results to the users, and then they have to modify, and then we're going to be exploring some techniques of after giving the solution, how do we let the experts modify it and kind of deal with under specified conditions. Yeah. So just to continue a bit about mathematical optimizations, Now, for linear programming is already quite expressive technique, and you can, and it's extremely mature technology. You can routinely solve problems with millions of variables, and yeah, like mixed integer linear programming and constraint programming are also quite. They are, you know, basically you can model almost anything with them, and they can also solve relatively large instances of many NP-hard problems, which are the ones that one finds in the industry normally. And this slides from certain optimization companies claims that the combined hardware and software speed up of mixed integer programming solvers is 1 billion, of which I think about 2,000, the factor of 2,000 is due to hardware and the rest of software improvements. So yeah, then yeah, we have convex programming. They're not as expressive as mixed integer, but it's also a mature technology. And it's one can approximate many problems, combinatorial problems as well with it. And it's a mature technology, and it's many problems in machine learning and statistics can be expressed as such programs. And then we have also, you know, in deep learning or yeah, for example, or other places, we have kind of non-convex problems where we're using some stochastic local search to find a good local minima. So yeah, we have this kind of and many more classes of optimization problems. And I wanted to say that basically it allows sort of an easy mode for solving business problems. So if you have a certain requirement and you're able to model it as an optimization problem, essentially you're decoupling the problem solving and the problem representation if you know how to represent and can identify you know, the class of the problem. And I just recommend, like, if some of you are interested, to just think of the domain of your interest and try to apply some of these optimization techniques. You know, R-Tools is like a nice Python library one can start with. It's already good enough to solve many problems, many practical problems by just kind of declaring and the variables and solving them. One theme in this talk is kind of the dichotomy between declarative and imperative, which would become apparent later as well. And so, I mean, one problem with this, with the process I outlined before, is that we basically do something like that normally. So we gather goals or preferences, specify action transition, specify initial state. So essentially, if you want to solve certain planning problem, which represents a process that some human is doing as their job, and you want to help them, you sort of, if you want to pose it as an optimization problem and solve it easily, hopefully then you do these steps and define some sort of dynamical system and objective on it, solve it somehow, and then give it to the human. So, I mean, so what I wrote is that you sort of create a plan, and then maybe the cows come home when you give it to your user, and they're expected to follow the directions that the plan is giving them. But sometimes it doesn't work. And so why doesn't it work? Basically, you know, planners are the user is committed by the specification they give you, and maybe they give you some hard constraints that are really softer, or soft constraints that are really hard, or they kind of are really, they're like something they just didn't tell you, so you have more constraints, or they just don't feel responsible for the product and don't believe things that don't match their intuition. So for any number of reasons, they might not follow these recommendations. And so there is, I started talking about the business, but the reasons, but the reason is not that they're stupid or something, your users. The reason is they are responsible for certain complex process, and they know what they do. And also human thinking, not unlike optimization problems, you don't have feasible region, okay, these are the states of the world which are acceptable, and I order them like this based on this optimization function. But humans think in terms of, okay, I do this and then that. So it's more like imperative program. And it's quite difficult to get like an imperative, like such a process, and turn it into a optimization problem or requirement set that fully describes it. Yeah. And so, there are these issues that, and it could be for any number of reasons. There could be data quality issues. These rules and exceptions are basically what people do. Then it's also quite the pitfall that it's this observation that if you just take a sort of random optimization problem, so a random region and then random optimization function, normally when you try to optimize it, it would go somewhere in the edge of the domain, and in some kind of very extreme case, is going to be the one optimizing this function. And extreme cases are like not so great. So in a sense, they lack common sense. This is kind of how this translates to math or requirements. And then, there is the question of responsibility, which is, extremely common. And we'll go over it in a little bit, like with a couple of examples outside of Transmetrics domain. And then, sometimes there are political games or political considerations or job security, which are not, however, the driving factor normally. And another thing I want to mention is that, when you model stuff as optimization problems, you also have local versus global decision-making problems. So a optimization could solve something on a global level and achieve the minimum objective, but normally many organizations work by giving local responsibilities, so decisions are being made locally, and then a global solution could be in stark contrast with the normal way people operate within their kind of place of their local responsibilities, let's say. So that's another thing which we need to consider when solving these problems. So just to mention about the responsibility and that it's difficult to trust black box machine learning models, there is, I'm going to go over two, by this point, quite commonly presented use cases. So this one is an example of a deep learning model classifying huskies and wolves. And upon analysis, and it achieves superhuman performance on this task on the train set and on the cross validations. But what it turned out after examining the results and the explanations under some measures you can read about here is that basically for wolves it was just classifying the background, if the background is snow. So this could lead to quite bad predictions if here you have a husky which actually does look a bit like a wolf, but because of the background is classified as wolf. So and it could be even kind of and the point here is that real world data is collected via some process, and if this process has certain biases included inside of it, or some confounding factors, statistically speaking, it could lead to a model, because like machine learning models at this point are normally curve fitting. So, you know, a machine learning model cannot distinguish between the sun rises and then the rooster crying. So which is the cause and which is the effect? It could just as easily say that the sun is rising because the rooster is crying as the opposite. So here we have this even funnier example with like a convolutional neural network which achieved superhuman performance in classifying pneumonia. And when they analyzed sort of the I think maybe it's the last stage, like so they use some technique for assigning weights to how different parts of the image influence the decision. So these numbers mean that, okay, if it's plus, then it predicts that it's higher probability for pneumonia, and if it's minus, then lower probability. And you can see here that it assigns a high weight for this part here, and a low weight for this kind of part in the lung, which does seem like some opacity, like pneumonia-like opacity. And what happens here is that it just is portable. So this X-ray machine is actually portable, and it was brought to the patient, which was, and the patient was supine. So probably they just couldn't move or are in bed, or so they're just generally in worse shape. So now the model is just kind of looking here, and if they see portable, then they classify pneumonia. But if this label is something else, then it's kind of screwed. So it's difficult to trust these things sometimes on accuracy alone. And it's like a general theme about sort of at one point there was this movement that all you need is data, and it's still correct in some domains. Like if data is like the way the data is being collected is completely representing the process of interest, and without biases, then all you need is enough data. But theory also helps quite a bit. And yeah. So, okay, so these are like the two medical use cases I mentioned. And yeah, like just kind of another perspective, maybe I'm repeating myself, but the difference between the model and the human planner could be summarized roughly as this, and like some of the reasons they don't like to use optimization proposed by us or somebody else could be that, you know, you just have this dichotomy that it's difficult to declare what states of the world are acceptable versus just this is what I do. So here you have to be quite clear about the preferences you have and like what's allowed, what's not allowed, whereas many times, okay, this is almost always not allowed, but it's allowed just sometimes. And if you cannot quantify what does it mean exactly, it's allowed just a little bit, then you just say it's not allowed. And then for this, it becomes a hard constraint. So if they violate it from time to time, this can lead to different results. And then, yeah, you just have to make your requirements explicit. This is another quite like a strong pain point that for optimization problems, you basically need to execute the solution fully or it doesn't make sense. Where people, when they wouldn't like to commit fully and give away responsibility to some algorithm, and they would prefer to sort of try something, execute part of the plan, then see what happens, then replan, and so on. So that's a better way to get compliance and make basically the product useful. And so because of these issues, there is the bias towards current modus operandi. And of course, there is also this just inertia of people doing what they've always done. So we have this bias towards current demo, and people want to sort of overcorrect the suggestions or
put sort of straitjacket rules, try to turn the system into Excel where they can just edit everything and don't actually use the optimization features, but just kind of use it as a calculator or something like that. And also there is this thing with excessive safety cushions where you need to be somehow risk averse, but this is not explicitly stated in the optimization. And also local agents would tend to be more risk averse than the organization as a whole. So you could have like some slight conflict of interest between the project sponsor, so to speak, or the person who's interested in having this project executed, and the local decision maker, just on the basis of risk averseness. They could have, different risk averseness between each other. And so, okay, we have like some small diagram about how this thing could work in theory. So we get data, we do some statistical analysis, we do some suggestions, and then the planner checks and provides the final decision. So they are responsible for the operational execution, because we have clients, we're not the company directly. And then so we want to provide the planner some tools to examine the optimization results, or the results, and then make them acceptable to themselves, and then help them execute. So we're going to talk about some techniques and tools, and they're both on the mat and the UI side. The general theme of this is kind of understand your problem, understand how you can combine data with theory. So both card data which is recorded and anecdotal evidence or expert knowledge, or just kind of theory in general, like about how the process of interest work and so on. And so I'm going to give small examples for probabilistic programming, for just kind of the utility of reporting uncertainty sometimes. Then I'm going to talk about a bit about local search, scenario examination, and constraint editing in optimization context. And a bit, well, I'm not going to talk about it, but there is an example of a gamification in the end, if you like to check it out. And SciML is this kind of is talking about general techniques for combining data and theory. If you, for example, with neural differential equations and stuff, which we're also not going to talk about too much. Okay, so case one. So we had this problem about where we had data about ordered items which are going into the trucks. And so for these items, we know some things, but not everything. So for example, by law, they have to record the weight, the sender and the receiver and so on. But sometimes they don't, or they very rarely record the dimensions unless they have some expensive machines, which sometimes, like normally, they don't have. And well, now maybe with vision and stuff you can do it, but they didn't have it. And then some properties of the packages. And then these things, this data is expensive to collect. So the dimensions data basically is expensive to collect. And it's needed for further analysis purposes. For example, if you want to know how full a truck is, so how much empty space there is, just from the loading list, then it's useful to know, or to at least have an estimation of the dimensions. And so we had this problem that basically we couldn't know how full the trucks are to continue with the rest of the things that we do. And we did this kind of process where we created a statistical model. The warehouse staff reviewed the suggestions, and then they could have some means to add some information that the model was, in their opinion, getting wrong. Then we refit the models, and after a few training sessions, we managed to have under certain KPIs reliability above 90%. I think this was measured by like total truck village in this case. So yeah, those are the benefits and the technique we used for that, and you could also like check it out if anyone is interested is probabilistic programming. So I'm not an expert on this, and I apologize to someone if I say something very wrong. But from user perspective, essentially what you do is you think, okay, what is the process that generated this data? You write a imperative program which tells you essentially what's the likelihood of observing some certain items, certain piece of data like a row, given the parameters you put in. And it does look almost like a imperative program. And then you use like sampling or optimization magic techniques to get a full or an estimation of the full joint distribution of the parameters of interest. What this gains you is that it's extremely flexible statistical modeling technique that you can use for, to describe quite complex processes which are not necessarily linear. You can handle missing data in a very flexible way, and generally just put a lot of theory together with data in order to do these estimations, and then you get like a full Bayesian estimate of your parameters, like you get an estimate of the full joint distribution in the end of it, at least in theory. And yeah, so for kind of tricky problems where it's not easy to like fit them, maybe there is not enough data. It's also kind of efficient in low data regimes. Yeah, it's good, and also generally produces at least somewhat interpretable coefficients that you can talk about with your expert users and ask them if that makes sense. So yeah, basically what we did is to receive these fields, kind of XYZ dimensions, volume, weight, stackability, other attributes, and arbitrarily many of them would miss in every row. I think for the dimensions, the data was about like 5% full. I don't remember exactly, but no more than that. And then in the end of the day, we provide, we could sample essentially dimensions which are consistent, like at least which are consistent with the rest, just data rows which are consistent. And now it's kind of similar to generating synthetic data. Actually, there are some some nice companies that do that, especially, which is important with the GDPR and stuff. But okay, so this was the task. What we did was to create, this sort of model learning this joint distribution with arbitrary kind of subset of the data missing in each row. And then we had sort of the users both examine the final results, so the package dimensions and certain other very easily according to us, and then explainable parameters, and they would sort of come back with stuff like, okay, this doesn't make sense, maybe you should adjust this prior like that. And after a few iterations of this cycle, we got something quite good. So yeah, I mean, you could try it out. There are these packages that are relatively mature, in my opinion. I haven't used Pyro and TF probability, but the rest I've used, and they have like their pros and cons. But yeah. So this is like one way to sort of have interpretable models and uncertainty baked in. So you can kind of, include quite a bit of prior knowledge there, and business, essentially like combining business logic and stats. Yeah. So the second example is actually, we haven't done that yet, but it's also inspired by a medical application. And by this ML community, the source materials by this doctor, you can Google him. So essentially, if you have a machine learning model, like a prediction-based model, you could use this rule-fit algorithm, which basically builds trees somehow, like with random forest or gradient boosting, which are still, I think, state-of-the-art for tabular data. Then it uses separate algorithm, which for converting these trees to kind of shallow rules, either like by taking them directly or by taking some subsets and pruning them further. Then these rules, either if you fit a regression model using those rules as features, which already gives you something interpretable because you can now label the rules and have like a certain amount of rules which are supposedly easy, or you can start doing stuff with these rules. So one thing is to ask, you could try to check how useful these rules are, and if they are like either bogus. So yeah, so the rules might be bogus because of some artifact of how the data is collected or something like that. Like I think in the medical context, there was this thing where if a patient is anyway, I forgot, but basically comparing what your expert users think about these rules, and also how the machine learning algorithm thinks about them, either by using some permutation type technique or directly taking coefficients from a linear model. You can throw away the rules with big difference between the two ranks, or otherwise examine them like they might tell you something important about how the data is collected, or about the biases that the expert user might have. And you can refit the last one. This procedure kind of gives you validated and both validated and interpretable rules, which uses features, and that's a good thing. And so now we are trying out this technique, and hopefully we start user testing in a couple of weeks for certain parts of our machine learning algorithms, and it already gives some promising results for modeling special events in a forecasting packages context. So yeah, that's another example. Like a third example, which is kind of simple, is simply to show uncertainty estimates for your target. So here, this is not from the system, but like a variant of this we have, where basically you show at each point a certain credible or confidence interval depending on the technique you use, and you just say, okay, in this kind of, whenever this is white, I cannot give you a very strong recommendation. So maybe the planner has some local knowledge, because when people are solving these problems, they actually have, they have less data than you, in the sense that they cannot look in the history, but maybe they get more data than you just by looking with their eyes what's going on in a warehouse or in certain, wherever they're working in real time, which you might get with delays, or just there could be some information you're not considering, because not everything is recorded. So yeah, this is kind of also recommended, and it does improve like basically trust, because otherwise when people say, okay, now this is deviating too much from the actual reality, now I don't believe you anymore. Whereas if you kind of tell them, okay, today I have low certainty, then you just then it's much better to just say what you don't know. Okay, so the fourth example was to have like for long-running projects which are not real-time, to have a sequence of business scenarios that you sort of go through, and like start with just the problem specified, solve it, and say, okay, if we, so this was like a client of ours, it was a consulting project, wanted to sort of change, maybe hire 2 or 3 more warehouses and change the operational hours for the rest in a network. And there are various operational considerations which are difficult to price one against the other a priori. So they just wanted to kind of a model to play around and see how different scenarios would perform. And so the way we started was to just model everything with the business scenario, with the requirements as stated. And yeah, create an optimization model, solve it, then report kind of very big potential improvement, which would imply normally that the business is very inefficient, which is, I mean, it's the case that it's not, it could be more efficient, but not by as much as this sort of greenfield model that, as I call it, is claiming. And then the next sort of part is to say, okay, let's put in all the operational, let's try to model your exact operational paradigm by putting more and more constraints into the model. So just whatever you do, tell us, and then we put it as constraints inside. And then compare the sort of how the cost, then compare the cost between the 2 things. And then we get something quite close to the accounting reality, yeah, within percentage points that could be accounted for by other stuff. And then gradually remove certain constraints out of them, just to see how things will change, and then remove the constraints that they are actually willing to change, because this one, like in theory, the greenfield scenario is in theory what they would do, but in practice it's very difficult, because when they see the solution, they say, okay, no, I don't do this, I do that, etc. So these were kind of the results. So firstly, we computed their historic scenario. So this was kind of from what they executed. Then the greenfield scenario basically kind of halved the costs or close to it. Then we added a bunch more constraints in the next stage, and we got sort of within, I think, yeah, within 9–10% of their historical reality. And then we sort of removed the constraints that they were most happy with us removing, and got like high utilization and lower costs overall for this project. So and this chart is just kind of showing more specific things about iteration 2 and specific things that we did there. So the theme here was that we sort of decided to edit the constraints with respect to the business reality. So we identified a subset of the constraints that need to be changed, and we did it and resolved the problem then. So this happened offline, but now we can also kind of put it as part of the product and try to do it online as well via some like tools. Because the problem is, even though the tools are quite mature, it still takes a long time to solve such a problem in many cases. Yeah. And then so in this case, we are now working towards interactive constraint editing, and just having the user being able to play with the model in a limited way, interactively, and yeah, online in real time, etc., etc. So basically, we solve the spec, identify a limited set of constraints with which the users can modify the requirements, and then resolve the model, and then report whatever is the relevant solution difference there is. So maybe they're used to always do something in a certain way. So they're like, okay, just do it like this. And then we report, okay, then the cost increases by this much. And or you violate these constraints, and then also the solution changes in this way. So yeah, I have like this example, this toy example we did for this purpose, because in the real system it's even more complicated. But basically, we have certain maximum flow or mean cost flow problem to solve, and we get some solution. And then we have some interactive question asking where somebody asks, okay, what about if you, what about if instead the flow between these two places is 300? And then we say, okay, no, that's fine, but then you're saving this much money, but you're violating this constraint. So you're not sending these items that you have. And so this is kind of work in progress, but we have it in a live system, and it's we're quite happy with like some initial tests that we're doing. And in terms of tools, yes, you have sensitivity analysis for LPs, which is not always possible. But with variable hinting and warm start features in constraint programming and linear programming solvers, you can get quite far with allowing the users to play with this solution like that. Another use case for this that we're so besides the sort of truck planning example is we have certain scheduling algorithms for which we also allow the user to resolve search solution close to what they have already to kind of the optimal one, but with the added new requirements. And yeah, this just gives like a very nice perspective, because then the local decision maker can make their local decision and then also see how this deviation from the optimum affects other stuff maybe far from them. So yeah, actually that's all I had, and I have some other cool use cases where I think this was sort of machine learning model that automatically again creates some. I think this one uses active learning in order to identify articles where it's most uncertain, puts them on some website and asks people to kind of rate if it's fact or not. So yeah, active learning is also a nice technique for this. And then takes into consideration this stuff. Takes into consideration the expert opinion on the articles selected. And there's some gamified versions of urban planning game. Sorry, like this is from a year ago. I looked at this example, so I kind of forgot what they are. But if you're interested, you can check them out. I think they're quite impressive. So I think that's it from me. So it's open to questions now. Oh, and of course, I have this summary that it's good if we can sort of get this symbiosis between expert users and optimization problems. And it's also, I didn't talk too much about it, but on the UI front also you have to think about like solution presentation, how to represent the exact solution difference, and just how to represent the relevant parts that could tell the user something, but you can only know it from problem understanding, both on the mathematical and the business side. So yeah, I think we have some job openings. If you're interested, go ahead. That's it. Yeah, sorry, Stefan, I forgot about the last few slides.
No problem, no problem. Thank you. Was very interesting talk.
Thanks.
And we have some questions. So, question number one. What's the percentage of accuracy which can be taken into account?
I'm sorry, can the person sort of specify this a bit? Because I
think this was relatively at the beginning.
What's the percentage of accuracy which could be taken into account?
Simeon. Simeon, if you read this, maybe you
can you please?
And we put it somewhere. I think it was beginning, but yeah. Then somebody said, awesome, with 3 exclamation marks.
Well, thanks. This is the level of specificity I'm looking for.
And then there is this question, how do you decide which factors to add to the greenfield in which order?
Yeah, so I think the greenfield basically, if you're going to do the whole process, you sort of what we did was to get all the requirements, like how. So the minimal subset of constraints which are required to run this business, and then solve with that, and then maybe they. So this is kind of the greenfield, yeah. And if you're going to do this whole process, I think this is the best way to start with, because anyway, after you're going to be adding a bunch more constraints. If you're not sure if you're going to be doing the whole process, all the way down to modeling the current business practices, Motomo, if possible, then you try to sort of if they're wondering about if this is needed or not needed, then it's better to include it. Yeah. If they're wondering about something, then probably include it. If you're not going to do the whole business, to do the whole process, but just modeling the optimization. If you're going to do the whole process, then you can exclude it and just leave the bare minimum, I think, and then explain sort of these are the current assumptions. So we're not doing this and this and this. If this is like a deal breaker, just include them after. Does that answer the question? Or
question, so I cannot answer for that.
Yeah, but if the person says I can.
Yeah. Let's see if somebody writes something. Okay, you said take into account the whole process. Do you have experiences how the models change if you only take parts of the process?
Yes, they can. Like the results you get can change quite dramatically, and yeah, basically, it could change in this way that it's not any longer modelable, and well, for example, it could I don't know, in transportation planning, it could happen that it's trying to route all the packages through a single warehouse, and then this one is overloaded, or it could just kind of cut away a bunch of trucks, but send many packages in like roundabout way. I mean, the solution basically can change a lot, both quantitatively and qualitatively. So you just have to kind of look kind of look at what matters for the customer, what matters for you, and yeah, that's about it.
So there is another thanks for the talk with a heart, and then there is a very nice presentation from Wojciech.
Thank you, Wojciech.
So, yeah, but these were all the questions. I think people are afraid of mathematics. So
No. I mean, the main point here was that you kind of, if you just try out using some optimization things like you can solve Sudoku very easily, or nQueens, or like some scheduling problem for your business, and you just basically write it down and it solves it for you at first stage. And the point was that there, I mean, for some of these techniques, you need quite a bit of math, but I mean, for the human in the loop part, but for just modeling and solving some sort of problem, I think there is a lot of low-hanging fruit everywhere. And yeah, if you want to discuss some like modeling some problem, you can reach out as well. So yeah, that was maybe something I wanted to get across. It's not that scary. It's you have this lazy mode kind of. So okay.
Okay, so thank you, Stefan, for this talk and for your time.
Yeah, thanks a lot. So do I stay here, or
you can
just
go
back
to the green room and
okay. Okay.
Yeah, and
bye. Thanks.
Bye.
Good luck. Thank you.
And in the meanwhile, people of WeAreDevelopers, we are coming up next with Svetlin Penkov, who will help us to debug machine learning code. This will be at 4:30, so at least enough time to grab a coffee, and yeah, see you then. If you wonder what to do in the meanwhile, you could also go to wearedevelopers.com and check out the nice jobs we have there. And if there is maybe your next career opportunity which waits for you there. See you then. So, hello, dear viewers. I'm back, and this means that you answered question in Slido. It is the "Have you ever broken part of your computer equipment in Tech Rage?" question, and at least 42% of you were honest and said yes, and there are 33% who say no. That's good. You never tried to program in Prolog, I think. And then there are 25% who are in the don't ask category. So basically, 2/3 of us broke stuff. I was also voting for a fourth category, and which said, please don't make me remember. This is the one where I would have been. But this being said, let's now go on and go to the stage to meet Svetlin Penkov for his talk about debugging machine learning code. Hi, Svetlin.
Hi, it's great to meet you guys, and I'm really happy and excited to be able to talk to you today about debugging machine learning code. Debugging is typically assumed to be a boring endeavor, but hopefully today I will show you how we can do it quickly and effortlessly, even with the most complex machine learning models. So a few words about me. I've spent a lot of time doing robotics and machine learning. I did my PhD at the University of Edinburgh in the UK, where I looked at various ways of bringing modern machine learning into robotics. And some of the biggest challenges there is that you never have enough data, and your models really have to be robust. A single mistake could actually endanger somebody. So the models really have to be well tested and robust. This work actually led me to join currently the biggest startup in the UK for autonomous driving, where I was actually the team lead of the motion prediction team. And our job was to come up with models that actually predict where agents in the traffic, including vehicles, pedestrians, cyclists, where they would be in the next few seconds, such that our vehicle can take the best decision. So I spent approximately 3 years or so with them, and last summer I decided it's time to go on the next endeavor. And this was actually starting a company called Cyber Research, where we started looking into ways of actually extracting computer programs from raw data. And when I say computer programs, I do mean like Python code or Clojure code or Go code or whatever you want from the raw data. But on this way of developing these models, we actually stumbled across lots of problems with developing and debugging state-of-the-art machine learning code. So hopefully today I'll be able to share with you some insights and showcase you one of the projects that we've been working on. All right, what do I mean when I say machine learning models and machine learning code and so on? So let's start from the basics. So when we say machine learning models, we typically mean some relation between some data, X in this case, which is the input, and some output data, Y in this case. And the machine learning models typically are some function F, which is the model architecture. It could be anything, neural network, Bayesian model, whatever. So this is the architecture of the model, this F function. And machine learning technically is about finding the parameters of this function, theta, that actually make the mapping between your input data to the desired target output data. So this is a machine learning model, extremely abstract, but this is what they are. This is the theoretical, more of a mathematical definition, but we as developers can look at this in a different way. So instead of thinking about functions, domains, codomains, parameters, when we develop these functions and these models, what we actually work with are two things. The first one is the data. So our input data, output data, parameters, all of this is data, and this data exists in our code base in some shape, be it CSV files, multi-dimensional arrays, whatever. So we have to work with the data. And the second aspect of machine learning code is actually the computation. So how do you process this data in order to get your output? How do you find the next best parameters to improve your model, and so on? So this is all computations, and this is actually the code that we write. So at the end of the day, when we implement machine learning code and machine learning models, what we do is we implement some computations that work with data, and this is pretty much it. But there is a twist when we talk about machine learning. It sounds very simple, computations and data, but in practice, here's what happens. What do we typically mean when we say a deep learning network trained to recognize an image? Well, here's the example of the computations that a fairly old now neural network is actually doing on the input images. So every single box you see here is one application of some sort of computation on the data. And as you can see, it branches, it has multiple layers, it has lots of structure. And writing this code is relatively easy, especially if you use some of the modern development frameworks, but actually debugging it is really hard. How do you, for example, debug something that's in the middle of this computational graph? It's a hard question. So we'll see how one can approach this. So the first step was computational graphs. They are complex. And the more exotic and the better performance models you get, they typically become more and more complex. At some point, it doesn't even make sense to try and draw the full graph because it's simply too big. Now, the second step was the data. And when we talk about modern machine learning, we typically mean machine learning models like neural networks or models that can be differentiated where we can find the parameters through backpropagation or something like this. And when we talk about such models, our data typically lives in some sort of arrays, or the technical term is tensors. And it's very often to work with one-dimensional, two-dimensional, or even three-dimensional arrays. And actually, it's even more often to work with 4 and 5D dimensional arrays. They come across quite often when you develop machine learning code. So the ellipses here is pretty important. So how do you even visualize, or how do you inspect the values of such multi-dimensional, big, complicated arrays? So these are the two main problems. But let's step back one step and think about the whole development process of actually any code. But in this case, we're going to think precisely about machine learning code. Well, the first step is when you have a problem, you think about what model and what architecture you want to implement. And you typically do some research, read some papers, then you pick an architecture and you implement this architecture. The result of this implementation is the code, and this is actually, the code represents the abstract mathematical definition that you had in your mind or you've written down on paper. It represents it such that a computer can execute this model. So once we have the code implementation done, the next step is to test its performance. So we run it on different data sets, we ask different questions about this model, and very often we find good results, but sometimes we don't. And if we have some problems with the performance, what we typically do, and it's a very intuitive step to be taken, is actually to go back to the whiteboard and rethink the model design, maybe from scratch, or maybe just iteratively keep adding something. This loop we see everywhere. This R&D iteration loop we see everywhere. We're very used to thinking about it, especially when we develop code and software engineering. The problem, though, is that the performance that we get is directly related to the problem that we care about and the model design that we've chosen. But in practice, the performance actually also depends on the correctness of our code. So when you make this last step from performance to model design, again, rethinking your design, you really should be asking first the question, is my code correct? Do I have any bugs in this? And you'll be surprised how often I see people in industry, in academia, who very quickly jump to a conclusion that their code is correct and then spend lots and lots of time trying to redesign their model, fight with the complex data they have, but it actually, very often, it turns out to be some bug in the code that they haven't had the time to look into, or they haven't even thought about looking into. So it's really important to ask this question first when you do machine learning code. Is my code correct? Only then you can go back to your whiteboard and rethink your design. Here is an example of exactly this problem. So what you see on this slide is a tweet from Andrew Karpathy. He's the AI director at Tesla. The tweet is from last December, and it says 2 hours debugging an issue I thought was due to something I misunderstood in the deep mathematics involved, but I just forgot to call model 0 grad. This bug really builds character. So you see here an expert in the field, a world-class expert who spent 2 hours, which is considerable time a considerable amount of his time, and he spent it thinking about the mathematics, thinking about the hard problems, thinking about the actual challenges in the model, without actually asking the simple question: is my code correct? And this is very common. We typically tend to focus on the hardest problems when we see an issue, and tend to forget to check the simpler, more actually common issues. So how can we solve that? How can we actually figure out a way to avoid spending time on such common but not so difficult bugs? Well, the first thing to have in mind is, instead of thinking about a single loop, a single development loop, you should be thinking about 2 separate development loops that are actually interconnected. So the first loop goes from your model design to your code. And whenever you have a bug in your code, at this stage of the translation of your model to the code, this actually leads to a semantic bug. And what I mean by semantic bugs, these are things that, for example, you ask the question, does my code represent exactly what I intend to do with the data? Or do I really understand the computation that's going on here? And is this really the computation I should be running on this data? These are more fundamental questions that you should be asking about your code. And very often they're really tricky to nail down, but can very quickly help you sort out your problems and come up with a solution that gives you great performance. The second loop that you see on your right in purple is actually the loop between your code and the performance, as in the tests and the actual running of your code. And when you have some bugs at this stage, we can call those bugs runtime bugs. And they can be lots of things, like you divided by 0 somewhere, you have a null value, you have an infinity value, you have an overflow, underflow, you didn't, you pass the data through a function, for example, that is out of the domain of this function. All sorts of questions that are really related to more to the data rather than to the design of the code and so on. But they also can deteriorate your performance significantly. So instead of thinking about one loop, you should think about these 2 loops and figure out how you can actually propagate your performance back to your model design. But remember that it goes back through your code, not directly. Right. So debugging is hard, and this is something that pretty much every practitioner programmer knows, and we've fought a lot with, spend endless hours trying to find bugs and so on. There is a really nice article I've shared with you here from the Association of Computing Machinery on the debugging mindset, and they have lots of interesting ideas and observations about how people approach debugging and what they do. But they have 2 very profound statements there that I would like to share with you today. And the first one is that actually it's widely known fact, and lots of people, when you ask them, they say so, that debugging code is often harder than writing the code in the first place. And this has to do with the fact that when you write the code initially, we have all our assumptions, we have the model of the problem in our head, like we have the mental state of the entire system and what we wanted to achieve. But then those bugs that are the hard ones, the semantic ones, they typically correspond to unknown unknowns. And it's really hard to find what you don't know. So this is one of the reasons why we believe that, and I also support this passionately, that debugging is often much harder than actually the first implementation of your code. And the second interesting statement, after having after interviewing multiple companies and teams, What the authors of the paper say is that, according to them and the people they've talked to, generally we spend more than 50% of the time when we develop a product, an algorithm, a model, whatever, on debugging it rather than on the first initial building. So this has lots to say about how we approach these software engineering tasks. They're hard, they're abstract. I think debugging is inevitable. We're never going to be able to nail down all the problems from the get-go. So we better prepare ourselves with the proper tools and efficient ways of doing debugging. So let's start with a very common problem in machine learning, especially when you implement something. It's a very common bug. I've fought multiple times with it. I spent endless hours and nights staring at plots and terminal printouts trying to figure out what's going on. So here is a tweet from Ferenc Huzar. He's currently at Cambridge doing interesting research on Bayesian machine learning. But one of his tweets, and it was actually quite recent, 2 weeks ago or so, or actually last month, I see. But his tweet said something along the lines of what you see here on the slide. How it started: when you start training your models, everything goes well. You tend to decrease your loss function, your training iterations go well, and suddenly you see a null value in your logs. And this null value means that something went wrong. There was a bug. You don't necessarily know whether it was a semantic bug or a runtime bug. And now you sit down and start asking questions. Okay, what was the most probable cause for this null value to occur? And you start running experiments and printing values and doing all sorts of things to see what's happening. But the key problem here is that there is no direct action that can reveal where was the none. What you can actually do are some assumptions and some testing to figure out where the none could be possibly coming from. So that's a big problem. So let's see. What are the common ways of approaching this problem and solving this bug? Well, the first one is trying to mentally go through the code, run it in your head, see if something's wrong. That's a very good start. And typically with this, you'd catch some very silly problems and it would be quite fast. But when it comes to hard bugs, we go back to the problem of unknown unknowns. Simply mentally verifying your code means that you're never going to explore something that's unknown to you. So this is why mentally verifying your code is great first step, but it works only for some of the simplest bugs. So we need to do more. What's the next thing that one can do? We can start inspecting variables and the state of our program to see what went wrong. We had a null value, so somewhere along the computation from the input data to the final loss value, that final output, there should be some operation causing nuns. So maybe we can try and find that. And the quickest way to do it is we just start printing values. There is lots of research on how people do debugging, and it's a well-known fact that more than 70% of developers do start with printing variables. And it's actually a very good thing to start with, just get a feeling of what's going on. What's the problem though? Why printing does not work well in the domain of machine learning? Well, here is a screenshot from actually a debugging session with IPDB. This is some data array here. And if you print the shape of this data array, you see it's a 4-dimensional beast. It has 4 dimensions and it's relatively big. I think it's several hundred, few hundred megabytes. And if you just print the data, so this is this P stands for print the data in the debugger, you get this. And you see the dots here because this goes for multiple screens of just some random numbers that are not even the whole thing. And you really don't get an idea of what's going on. What's the structure of the data? What happened? Where was the none? What could be the problem? All you see is just some numbers that are really hard to debug. But you would be surprised how many people I've seen, especially in academia, who spend hours and hours of staring at those terminal printouts trying to figure out what's going on, because they often work with very complex maths and it's not trivial of how do you solve the problem. And another thing to point out here is that this screenshot is from a debugging session. This is IPDB. And whenever I talk to people about debugging, they just say, you know, this is just some code, you debug it. Fine, you debug it, you fire your debugger. But actually, debuggers depend on textual representation of your variables. So you're again stuck at the problem of how do you explore this four-dimensional array in this case. Not a trivial task, definitely not a trivial task. So debugging in terms of printing is hard. It might work if you have a very good idea of what's going on and you can precisely nail down up to like 10, maybe 100 values where the problem could be, but it takes a lot of time as well. So what else do people do? Well, something else you can do is you can do plotting. This here, for example, is a screenshot from a really great tool for logging and plotting your experiments called TensorBoard. It was initially developed for TensorFlow, which is the one of the most famous frameworks by Google for deep learning. And this tool is absolutely great. You should definitely use it if you're not using it. It allows you to log lots of results from your experiments, and it gives you very nice interactive plots of all the log data that you have. What's the problem? Well, the problem is first, you have to know what to plot. So you can't just simply plot everything because it doesn't support it, doesn't work like this. How do you plot megabytes of data of individual elements? And the second problem is that you're only constrained to 2D or 1D plots. Here, for example, you see a 1D plot of probably some training time versus loss. Oh yeah, this is the cross entropy. So plots like this, or you can do some 2D plots. You can do a few things with plotting, but again, you only limit yourselves to a few plots, and you want to say what's going on with my huge computational graph at the backend with the data that's typically megabytes and hundreds of megabytes. So it's also not great, especially if you're working on a semantic bug or a bug that's trickier to catch. Plots would just tell you there is something wrong, but won't help you figure out where is it. So the next thing to do, and the last actually thing that I know of that's currently available that people can do, is you can sit down and say, okay, I have a really hard problem. It's really important to solve it. So I'm going to prepare a custom dashboard with some custom visualizations where I could very quickly see different dimensions, different items of my computational graph and so on. And this is great. This is absolutely great. In fact, there are already some tools that allow you to do this faster, but still, you'd have to spend a few days to build the tool, and I think a couple of weeks to figure out what exactly you need the tool to be showing. And suddenly debugging those models takes, instead of hours or a few days, it could easily drag into weeks, which is a big problem, especially when you have some deadlines to meet. And the other problem is, okay, you would spend this time, you'd have the resources, you'd have the time, you spend the time to develop those custom visualizations, you solve the bug, everybody's happy, and then in your next project, you encounter another problem. And the visualization tool you built for the previous one typically won't scale or transfer to the new problem. So that's this means that these visualizations are extremely importable. You can't move them from different projects. So yeah, they also take lots of effort. So there is a big problem that I'm trying to show you guys. We don't have sufficient tools to do debugging efficiently, especially in the context of modern machine learning code. This means huge computational graphs with megabytes and gigabytes of data. It's hard. And I have lots of experience of deploying those models on actual vehicles and actual physical devices. My previous team, we managed to get our models directly onto the vehicle that is currently roaming around London. And being driven by one of those vehicles where you have written the code and you're not sure how extensively you've debugged or tested the code, it's really nerve-wracking. So this indicates another trend. Machine learning now is at the state where it could bring lots and lots of value to the real world, but to bring it robustly and stably, we do need the proper development tools. And if you look into any industry that actually has a significant foothold in the real world, they usually have amazing tools to do these things quickly. So this is one of the problems that I came to realize more and more while working on various projects regarding machine learning. And that's why me and my team, we decided to figure out how to address this issue and came up with a debugger that we call fMRI, which I think is the first of its kind because it tries to show you everything in 3D such that you get a very good understanding of the data regardless of how complex it is. And it draws all the computations and everything that you could want into a visual UI that you can explore quickly, while you only having to put a couple of lines of code. So let me show you how this works with a couple of slides, and then I'll also show you a quick live demo. So let's start with the printing. Let's see if we can print a tensor or a multi-dimensional array. In this case, this is the code that we're going to work with, Python, very standard Python with some NumPy. So we're going to say we want to create multi-dimensional array with shape of 10 by 5 by 3 by 7, so 4 dimensions with these sizes. And just to make it interesting, we're going to create this multi-dimensional array from two components. The first one will be a gradual increase from 0 to 1. That's going to take exactly the number of elements of the array to go from 0 to 1. And we're going to put it in the final shape that we want, the 4D shape. And the other component will be just some noise. So we're going to insert some random noise again with the shape of 10 by 5 by 3 by 7. And if you print this, you're just going to see a huge list of numbers, not even a full list of numbers, and you're not going to get a good idea of what's going on. And exactly, precisely if you don't know the data and you just print it, you would have no idea what's going on. So how can fMRI help in this case? Well, the first thing to do is we import fMRI, and I'll just keep referring to it as EF. And the second thing to do, and this is the first building block of fMRI, it allows you to inspect all sorts of data by essentially saying EF inspect, and you give it the date. There are lots of arguments you can add for different bells and whistles, but let's start with this. Now, this is your code, and the way fMRI works, you need to start a local daemon that runs a visualization server, and then you simply open up your browser, go to fMRI.com where you launch the tool, and you can actually start exploring your data. And in this case, what you would see is the visualization of the data. So this is a direct screenshot of the tool, and there are a few things going on. The first one, on the bottom left, you see that we have the execution menu. Since this is really a debugger, we can pause or continue the execution of our code. In this case, inspecting simply prints or visualizes the data and proceeds with the execution of the code. On the top left, you see various things that you've inspected. On the right, you see lots of statistics about your data. You see a histogram, you see the shape, and actually here you can also play with the shape so that you can visualize it easier. In fact, fMRI allows you to visualize up to 6-dimensional tensors, a cube of cubes. In this case, we have only a 4-dimensional tensor. So we can do a few things to visualize the whole thing easier. So one thing you can do, you can just watch at the view dimensions here. These are just things you do with your mouse to drag the numbers around. We can unsqueeze or add an extra axis to actually remove the overlap of the individual voxels, and now you get to see every single element in your tensor in pretty much a couple of seconds. And we can go on and just do a few more transformations until you get the perfect view of every single element of your huge tensor. And now you won't have to do any guessing or assumptions about your data. This is your data, and you can really quickly see it. And having the ability to quickly test whether your assumptions about this array or that array are correct means that you'll be moving much, much faster when you develop your models as well. So this was the first step. This was the first stepping stone of having great debugging experience, being able to explore the data. You can explore the raw data, but in practice, we do recognize the fact that the data always stands for something else. It represents something. It could be just a pile of values, fine, But in practice, it could be an image, it could be a probability distribution, it could be lots of different things. And Inspect supports a few views where you can just say, I want to visualize, for example, here on the slide, you can see I want to visualize this array, which is technically a three-dimensional array. I want to visualize this as an image, and you quickly get to see what your data looks like in the domain that you care about the data, not just in some raw array representation. Okay, let's move on with more interesting example of how you can use fMRI. So I've shown you how you can explore your data easily without any problems, really quick, really fast. The next question is, how do you explore the computations? Remember, we had data, and now we talk about the computational graphs. And to show you an example, we're going to consider convolutional neural network. It's a very standard model for recognizing, doing machine vision, extracting various objects, answering different questions about images. In this case, this is a classifier where the network has to classify what object is on the image. And here you can see you have the image on the left. We pass it through some convolutional and ReLU layers. We get some intermediate data. We pass it through some pooling layers, some more intermediate data, and so on. So this is a very schematic representation of what a model looks like. So let's see. With modern tools like PyTorch, it's very easy to implement this model. So I'm going to walk you step by step through this implementation, and then we'll actually debug it and we'll see it live running as well. So implementing a convolutional neural network is one of the, in fact, the tutorials for PyTorch. We're going to do something very simple. And the way to do it with PyTorch, for those of you who don't have much experience with this, you just import the necessary modules and you derive from the NN module. And now you can define any machine learning model that you want. In our case, it's going to be the convolutional network. And to do this, we're just going to create two convolutional layers. You can see them here and there. These numbers here, they're just parameters for the layers, how many intermediate masks they generate, what's the size of each kernel. These are lots of details that are typically important when you do the design of these models. But now I just want to focus on how can we debug this if there is a problem. The next thing to do is we're just instantiating one max pooling layer and then 3 fully connected layer. That's what the FC stands for, or a linear layer, which is the more common name. So this is the initialization. This is saying this is the sort of operations our model would be applying. Now the next thing to do is just to say how we're going to apply these computations. And the way to do it is we just continue the definition of the convolutional network class, and we just write this forward function. And the forward function takes your input data x, and here you see very well what's going on. The first thing x, we pass it through the first convolutional layer, we pass it through the ReLU layer, then we pass it through a pooling layer, and we just keep adding these computations. Here in the middle, you see a reshaping of the data. So before, up to here, the data is actually a 4-dimensional array because we have multiple images, and each image is of 3 dimensions. So we have a 4D array, and it's a very typical thing to work with for 5D arrays. So here we just, in order to be able to feed it through the fully connected or the linear layers, we need to reshape it into a 2D array, and we just pass the data until we just return the final output of our model. So this is a very standard, fairly basic model. This is something, if you have experience with PyTorch or any other framework for developing these models, it's very intuitive and very quick to do. Now, once you have implemented your network, your question might be, okay, I want to train the network. And to train the network, you typically have some code looking like this. I've omitted some details that are just not interesting. For example, loading the data from the disk and putting it in the right shape and so on. But essentially, at some point in your code, you're going to have this training iteration loop, which loops over your data. You tell the optimizer, this is the object that learns or updates your parameters until you find the best ones. You tell it to just reinitialize for this iteration, and you pass the data to the model. This automatically calls the forward function that we implemented and gives you the output. Then here, this cross entropy function is a loss function between your output and the target. So this is actually the difference between what you expect, the target, and what you actually get. And based on this loss function, you do backpropagation, or you just calculate how should I update each parameter such that my output gets closer to the target. And you just say, okay, I know how to update my parameters, so do one update. So this is it. This is what the standard training loop looks like. And now what if we want to visualize all the computations that went in here? How do you do that? If anyone knows a way of doing it without the two I'm going to show you now, I'll be more than happy to know, because I'm really curious to see other ways of doing it. So what I'm going to show you now is through something that we call scanning. So again, we import fMRI, and fMRI, we have the idea of scanning. So you can put your training code, your core of the training loop within this scan statement, and what this will do is it will keep track of every single computational step that you execute within this with statement. It will keep track of all the data. It will keep track of any problems that might occur. You'll see an example of this as well. And if you run this code now, what you get is actually this. What you see here is, again, a screenshot from the tool, and you see the computational graph exactly as we had it in the code, visualized in fully 3D, where you can play with it. And what do I mean by the computational graph being visualized? Well, you can see the direct correspondence between this input here, this big box of grayish voxels is actually our data. Then our data is fed into our model, and you see this here. And then the model outputs something. This is the output. We compare the output with the target, which you see here. We put it through the cross entropy function to get the final loss. So you see a very direct mapping between every single data and operation you do to the visualization that you get. This backward pass is something that allows you to visualize the gradient, or how you should be changing the parameters. I'll show you the data, how it looks like. The graph is the same, it's just there is more data associated to the graph. So now that we know how this visualization maps to the code, we can ask the question, okay, I know that this forward pass of the model actually calls a complicated function that's actually the convolutional network. Can I see it? And the answer is yes. fMRI, being a debugger, actually keeps track of all the function calls and the stack frames and everything you needed. So all you need to do is just double click on this, on this blue box, and what you'll see is the visualization of the entire convolutional network. So now here you start seeing what we wrote in the forward pass of the function. We had the convolutional layers, ReLU layers, max pooling, and so on, but now in a very intuitive way where you can explore things and see what's going on. The blue cubes here in this case are the inner function calls. Even though our scan statement was at the top, we keep track of all the inner function calls and the intermediate values of those functions. We can keep going. Essentially, depending on your implementation, the code, and the library, you can keep going and expanding functions. And if you expand this function, it's actually an interesting one. This is one of the convolutional functions. And if you expand it, you get its input parameters, and parameters in fMRI visualized under the function. So you get an idea of what do you train, what's the data, what are the problems with the data, and so on. So we can keep expanding and getting different parameters and exploring the model. These are the gradients now. You can just press G or one button, and now you can visualize all the gradients that your code calculated, and you can quickly see what's going on. You can do batching, lots of different things. I'll show you some of these in demo that follows. When I talk to people about fMRI and I show it to them, they're very concerned about scale and whether it works with big models. And in fact, with our tests so far, we've tested with some of the biggest models. And here you see an example with one of the biggest open source models, VGG19, with almost 150 million parameters. And you can visualize this on a laptop in a few seconds. So you shouldn't be afraid of trying to use the tool on your models, regardless of their scale. Because they're efficient, you can also do interesting real-time visualizations. This was just us putting the scan statement around this variational autoencoder and just visualizing the values in real time. fMRI also works with all sorts of complex graph architectures. In fact, as long as you can express your code as Python, your graph as Python code, we should be able to visualize it for you. And I guess the last interesting feature, which is probably the most important one, is assertions. When you think about code and software testing, we put lots of assertions in our test files and we write tests and so on. But for machine learning, we haven't been putting any effort into this direction as a community. And fMRI is probably the first tool that addresses this problem. And it allows you to express different assertions in terms of your data or computations. And you can automatically execute those assertions at different stages of your scan, after the forward pass, before the backward pass, and so on. So let's see an example of what happens if you deliberately put some infinity value in the input of the model. So we corrupt this tensor, and we tell our code, yeah, just run with this while we're scanning it. And what would happen is the fMRI would automatically detect, look, there are none values and infinity values we've detected. And here is the computational graph. I'm going to pause the execution of your code so that you can explore the exact causes of this problem. And you can see very well how this single infinity value propagates into a patch and then into some pattern, and then eventually it just becomes non-values. And now here you actually can see the cause of this problem. So this is a very powerful way of quickly saving time and just figuring out what went wrong instead of you hypothesizing. You can also detect these non-infinity values in the gradients. Everything, all these things are built in, so they're very quick to use. And if we go back to the comment that Andrew Karpathy from Tesla had a while ago, if he was using fMRI, for example, he would immediately get this error saying, look, we've detected some non-zero gradients before training. Are you sure? Yeah, just have a look and figure out what to do, because sometimes this might not be an issue and you can disable it, but yeah, most of the time it is. So there are multiple reasons you would want to try fMRI out. If you do research, you'd get much deeper insights into your models and what's going on. If you develop code for the industrial standard code, you tend to do it much faster, and you're going to avoid lots of common bugs. And also you'll be able to test and iterate much faster with your data and your implementations. So now what I'm going to do is I'm going to quickly share a quick demo in the next 5 minutes or so of fMRI in action. So what you see here are two things. Split screen. On the left, you see the actual fMRI website. On the right, you see a notebook that I've started on my local computer. And I've also started the fMRI daemon. So I've done those two steps, and the next thing I need to do is just simply go to the website and launch the visualization tool. So now this visualization is listening to whatever is happening in this notebook. And the first example I'm going to show you is we're going to load some data, a tensor from some file, and we have no idea what this data is. And we want to get a feeling of, is it okay? Does it have some invalid values and so on? So the first thing to do is we just print the shape and the size of this data, and we see it's a three-dimensional tensor, so it will be tricky to print or even visualize with matplotlib or some of the other standard plotting tools. And it has almost more than 7 million elements. So yeah, it will be tricky to see what's going on. We might start doing things like, okay, what's the minimum value? What's the maximum value? I want to do some slices and see what I have in the slices. But this will only take you so far because you actually have 7 million elements and it will take a while. So another way to do it is just to tell fMRI that you want to inspect this tensor. And what happened now is I run the code, and now you see the data in the visualization. So this is the full tensor, and I can zoom in, and by me dragging the mouse, I can go into individual voxels. So the first thing to note is that yeah, everything looks black. So everything looks like yeah, there's not much going on, and I can also just drag my mouse on the surface of the tensor. So why not? Can I actually see what's happening within? And you can, very easy. You just enable the intersections, and now you can start doing sweeps of your data. And it turns out this data that you've loaded actually has lots and lots of structure that we managed to capture really, really quickly without us having to spend hours of figuring out what's going on. So yeah, here you see, for example, visualization of an MRI scan just because it's a multidimensional tensor. And you can visualize any sort of data you have as long as you can put it into a tensor or NumPy array or yeah, any sort of array, in fact, for Python. So the next thing, I'm going to show you the visualization of the convolutional neural network. And actually, I'm going to show you the model that I started working with when we were developing fMRI. And this model, if you run it, so I just loaded the CNN from the slides and the data. And if you run this model, after only a few iterations, you'll actually start getting nuns. And me and my team, we spent a couple of debugging sessions trying to figure out what's wrong with this model. And the thing is, we couldn't figure it out. We tried lots of different things, but yeah, at the end, we decided this is the perfect candidate to try and debug using fMRI. So what we did, we just put this model aside and we continued the development of fMRI. And especially, we continued the development of something that we call the assertions library. So this is a full predefined list of all sorts of assertions that could break if you have some issues with your code that are typically very common, like non-zero gradients or non-values or infinity values and so on. So we're going to run the same code, but this time we're going to enable the full check. So we're going to tell fMRI, check every single assertion you can for this model and tell me if something's wrong. And we're going to scan the code. So now, if I run this, what we see on the left is actually the computational graph. And this is exactly what we had in the slides. I can make this a bit bigger. So I can say this is an image. So I want to see it as an image. Let me see what's within the network. And here is actually the convolutional network that we define. I can click on expand different parameters and so on. But important bit is what it says on the bottom left. On the bottom left, it says that just after the backward pass, we've detected a violation of the assertion that checks for vanishing tensors. This means that a tensor is essentially zeros, all zeros, and this is after the backward pass. So this means that this is technically the gradient. And here is the gradient. I just quickly switch to the gradient view. And if I go here, you can see on the right, the histogram for this thing is essentially zeros. And this was the first error that we didn't see and we didn't anticipate at all. But if you continue the execution, so this is just after the backward pass, but if you finish the entire iteration of the forward and the backward pass and update the parameters, what you're going to get is another error, which if you hover on it, it says invalid positive inputs detected. And this is just an assumption that we know should hold true if you're doing classification. You typically talk about probability masses instead of probability densities. So this means that probabilities cannot be more than one. And if you take the log of this probability, it cannot be positive. And what happens here is that this assertion automatically found the problem. And the problem is that in this NOL loss function, negative log likelihood loss function, we are feeding positive values. And we even have a tooltip of what you should do to fix this problem. In this case, just put a cross entropy function or softmax. So you see how quick it is to find very common but annoying bugs that sometimes are really tricky to get because you never think about them. And just to finish, I'm going to quickly show you another example of a pretty big model. So I'm going to show you the ResNet 101 model. So to do this, I'm just going to stop this. And I'm going to run the model from a local file. It just I don't have it in a notebook. So what's happening now, I'm running the model on my machine, doing the first iteration. And what we should see in a couple of seconds is the visualization of the entire ResNet 101. So here you can see on the bottom left, it's loading because now we're talking about hundreds of megabytes of data that's being first traced automatically and then visualized. So here the model in this case is applied on the ImageNet competition. So the ImageNet competition is you have lots of images, pretty big ones in terms of machine learning data sets. And you have to recognize 1 out of 1,000 classes. You can see here the output shape is 1,000. And we can start exploring what's going on. Okay, I've just expanded the first function, and we can now actually look into our model. And our model looks interesting. It has a few very big tensors in the middle. These are the convolutions typically. And you have the output linear layers that overpower the whole thing. But now, because this is a trained model, I can, for example, show you very quickly. We can go and see what the convolution and the first layer learned. And this is a very well-known result in machine learning and computer vision, that the first layer filters that you see here, they actually have lots of structure, they detect edges and checkered patterns and so on. And a couple of years ago, this was several papers, and it's a very interesting phenomena. Now you can just observe this in a few seconds with even with some of the most complex models. And yeah, you can explore a lot. The really important bit is that you should have a question that you're asking, otherwise you're going to just drown in that much data that we can show you. So the last thing I'm going to do, it's never going to be useful in real life, but I'm going to expand the full model. So I'm going to show you the entire computational graph of the model. Pretty much me going and clicking on every single box until I reach the bottom of the call stack at every single function call. And what you see here, this is the full ResNet. And as you saw, we just visualized it in a couple of seconds. And yeah, you can now zoom in and start asking questions. And now you actually get a very good idea of the complexity of the computational graphs that we deal with when we talk about modern machine learning models. Yeah, let me just rotate this for you. And yeah, it's pretty big. And yeah, you have to be able to carefully choose your questions, to make this work for you. So that's pretty much everything I wanted to share with you today. How does it work with the questions and answers now?
Well, this is simple. I pop up the Stefan tensor, and let's have a look at the questions. Okay. Is processed data communicated to the web page, or is it the original data?
Yes, no data leaves your computer. So all the data that you see visualized is the data from your code, and it stays within your computer and within your network. So you shouldn't be worried about any confidentiality issues or privacy issues and so on.
So basically the visualization is in the web component.
Yes.
Yeah, okay. That was question number 1. Question number 2 is a comment. It says, yay, demo. Okay. So that's all the good questions you could come up with, guys. Oh. Okay. How long did it take you to develop this debugging tool?
Yeah, so the idea about the tool, I think it's already 2 years old, and we did some initial tests in terms of like what technology is the best thing to do. Going from I know what to use to actually what you saw today, it was roughly 12 months of our team working almost full time on this problem. We've developed some pretty interesting things like using those multidimensional tensors very fluidly in your browser requires lots of engineering and getting around WebGL and doing quite interesting things with shading and so on. And in fact, I think right now, if you want to visualize voxels and 3D data, I think fMRI is currently the most computationally efficient rendering engine.
So some questions came in afterwards. One is from Wojciech. Do you share the debug tools through pip?
Can you repeat that? Do we share?
The debug tools through pip?
Through pip? No, actually, currently the way it works is you can register on the website, and that's how you get access to the tools. As we are spinning off from our main company, this project, and it's becoming its own company, our path is to turn this into an open core product. So yeah, it will take a while, but soon it will be freely available through pip, and hopefully you also have the core released fully open source.
Very cool. Okay. Anonymous says, this is mind-blowing, exclamation mark. And in brackets it says no question.
Good. I really love it, because initially when I was talking to people about debugging in 3D visualizations, they just didn't get it. And now when they see it, it's really nice to actually see people appreciating and seeing how much effort they can save.
Yeah, I also like the small recommendations which are coming up in the box in the corner.
Because many of those are just things that if you are extremely diligent and go step by step and check every single box, you will find it, but you never do. So
True. Okay. And another question from Anonymous. If this is first such a debugger on the market, how others are dealing with debugging machine learning issues without such tools?
how are others dealing with debugging issues?
Yeah.
Well, from my experience in both academia and industry, in machine learning and robotics, I can say that the way we dealt in industry so far is we would just put a team staring at printouts and plots for as many hours as needed to figure out what's going on. There are lots of tools for tracking experiments and logging experiments, but I'm not aware of tools that actually help you do this debugging. And this is the sole reason we decided to do it, because we just needed something like this.
Yeah. And to actually see the bug where he is. So
yes,
you have a chance.
Yeah.
Okay. So I say thank you. And I'm looking forward to have you back at this show once you are settled, or once you want to promote the open source part of your product.
Yes, that would be absolutely amazing. Yeah. Well, thank you very much as well.
Thank you.
Enjoy the rest of your evening.
Thank you.
Bye-bye.
Bye. So, and we will be back in a short amount of time with how to build a food delivery app using location intelligence and matrix routing with Dosana, Olivia and Jose. So this will be interesting one. See you then. So, hello again. We are back with all these people from TomTom, Dosana, Olivia, and Jose, and they will tell us how to build a food delivery app with location tech. Hi, guys.
Hello.
Hi.
Hello.
So, your show. So, I will turn off my microphone and camera, not be in the way.
Okay, great. Well, I'll just get started then. Thanks for joining everyone on with us on how to build a food delivery app. And today I have my colleagues with me, Olivia and Jose. And we are actually presenting from 3 totally different locations across halfway in the world. We have Olivia in Austin, and we have Jose in Amsterdam, and I'm in the Bay Area. So 3 different time zones. And as you've guessed, we're all working from home, like many of you. And the pandemic has really just changed the way many of us live, eat, and hang out with friends, or not hang out with friends. Can you go to the next slide? Yeah. So we are working from home, and if you're like us working from home these days because of the pandemic, then perhaps you're also ordering in a lot. And like me, I am ordering a lot of burgers, poke bowls, and boba. So definitely not going into crowded restaurants, and as it's getting colder, we won't be able to eat outside either. And also I'm getting groceries quite often as well from Whole Foods, for example. And it's not just me or you, if you order quite a bit too. Investors are also catching up on this trend. In 2020 alone, and 2020 is not even done yet, VCs and consolidations have poured in over 13 billion into the food and grocery delivery startup scene. Meituan, which is the largest online and on-demand delivery platform based in Beijing, also just reached a valuation of over 100 billion this year. Of course, they do food and grocery and some retail, but it just shows you, I guess, the scale of this world. And in fact, McKinsey also estimates that this is an $83 billion market. So we've really just scratched the surface of food delivery, and it's only going to become more a part of our norm as we enter into post-pandemic, hopefully. But how easy is it to build a food delivery app? Can you go to the next slide? Yeah. So first of all, you need a customer-facing app where customers can see what restaurants are available around them. So you might have used this. You can pop it up and see all the restaurants, but it's not so simple as, what's close, what is the radius around you, and what are the restaurants next to you. It's also about how long it actually takes from a driver to get from a restaurant to where the customer is. So if there is a mountain, for example, between the restaurant and between the customer, what looks like on the map, just a 3-mile drive could actually be a lot longer. It could take an hour if there's that mountain, you're circling your way up and down the mountain. So secondly, you would have a fleet management platform that ideally oversees the driver routes, plan them out if they're not already automated, assign drivers, make sure there's support if the driver gets lost. And sometimes this matching and planning is a bit more manual, or it also could be very automated through an algorithm. So it kind of depends on how a food delivery service is set up and how much money and funding they actually have as well. And third, you would need an app for your driver so that they can see which customer and restaurant they're assigned to. And ideally, the app can also route them to the different locations, give them an ETA, track where they are, and give updates to the customer, to the restaurant as well. And then finally, you would need a restaurant platform that's primarily for confirming and taking orders, setting up the restaurant account and coupons, whatever. And ideally, the restaurant can also see where the driver is so that they can streamline the delivery handoff process But despite all these different parts that I just mentioned, so it is quite many parts, the main question for a food delivery app or service is, how do I optimize the delivery route? This is the big question and kind of the key to really a food delivery service. And it is a trifecta of 3 different stakeholders. You have the customer, you have the restaurant, and you have the driver. So who should I assign this driver to which customer who's ordered from this specific restaurant so that the customer gets their food on time, so that the driver has a smooth route and is always busy, so that overall costs per fee can be reduced. So this is the engine that really generates all the other parts of the app because it affects ETA, it affects cost prediction. So if you have an inefficient matching of your driver to the different orders, for example, when the driver's backtracking all the time, it's not a very smooth route, then you're really wasting your driver's resources and also your own. And then depending on how you pay your driver, if it's a flat fee, so, or if it's based off of a variable fee, so distance times time, not getting it right can mean that you're either overpaying your driver for a route that can be improved, or you're underpaying your driver for a route that really took them a lot longer than they expected. And so in all cases, not having an optimized route really means you're not meeting ETAs, you're gonna have very hangry customers, and you're gonna have disgruntled drivers that can switch between apps all the time, and you're operating at a potential loss. So we know that this is very significant. But how difficult is it to optimize the route? Well, it can be quite complex, and we know that because there is a 70-page research paper out there on how this actually works. The meal delivery routing problem, there is a paper by Georgia Tech on Grubhub's delivery routing model, and it is pages and pages of calculations and algorithms and decision-making models, statistical data, just how decisions can be made and the best algorithms in certain circumstances to show which route that driver should actually take to which customers and for which restaurants that the customers have actually selected. So it is complex, and it can be, but it doesn't have to be. And this is where, like location tech companies like us, TomTom, really come in. And thankfully, we can do a lot of this work and heavy lifting with APIs. So for each part of the process for the food delivery, from requesting the service to matching the drivers to navigating and tracking, to notifying when the pickup and drop off has happened, we can do that with APIs, and there's APIs all along the way, at least from a location tech point of view, to support this. And a lot of these APIs, at least offered by TomTom, are already souped up with the TomTom location technology. So we have a lot of the live and historical traffic data that's bundled into the API. We've even embedded a lot of the detailed road data as well, such as like curvature, how hilly it is, things that you wouldn't really think of that really matters to how long it would take and the selection of the best route. And we've also taken a lot of those complex calculations and just kind of years of experience, and all our engineers have bundled it into our routing API, so that our algorithm is already selecting the best routes for the delivery. And just to kind of simplify it all for an easy build to a food delivery app. So today, that's what my colleagues, so that's my intro, and that's what my colleagues will take you through today. They will show you what kind of APIs you can use, what location tech you can use, and to build a basic food delivery app for yourself. So I'll hand this off to Olivia, who will get you started.
Thanks, Dosana. So as Dosana said, Jose and I will go through a little bit more of the technical portion. So now that we have an introduction to what goes into building small service delivery apps and what makes them important, we want to go about the building part of it. During the worldwide pandemic, there's been obviously a huge demand for all kinds of delivery services in terms of development and projects that people have undertaken as well. So if you want to follow along or get inspired to create your own project, we suggest you think of the one thing you haven't managed to maybe get delivered in your area and start there. And we'll suggest building a food delivery service. We'll take you through an example using the TomTom APIs so we can see how a functioning prototype is built utilizing a multi-stop short-range delivery. Jose, did you try to say something there?
No, it's okay. Yeah, food delivery. Please.
Food delivery. So we'll start here. So our first and simplest step is to use the map styler, which allows us to export a cohesive map layer with our own custom style, which is on the developer portal. You would start by creating an account, generating an API key and using the map styler. And you'd have a section which looks a little bit like this. And this part tells you about the different automatic styles that are available before you start customizing the other parts of your map. You can work with the map layers directly to adjust and create lots of wacky colors if you like to. We've even published a few blogs on, Halloween mapping and other things like this. But for this example, we really want to use the specific traffic incidence layer flow within the map layer to enable traffic on our map so that we can really optimize our delivery and allow for other factors. And the map itself looks like this. And you can see the 3D renderings of the buildings, as well as some of the traffic flow down here. You'd be able to add contrast to see other features more clearly, like national parks or other demarcated areas. And when you're finished customizing, you can simply export and add the map to your project directly. And again, it doesn't necessarily have to look like this. It can look like any of these other styles or any colors that you customize and create for yourself. And that's the step that we pick up here in terms of the exporting and adding to your project. And this is where we start to get into a little bit of code. We do have some basic snippets, and I know that we'll also link to a GitHub at the end. And Jose will talk more about that as we get into the demo portion. But we do show some snippets just so you can sort of follow along and get a basic idea of where we are as we start creating the project. In code here, this is a pretty basic example of how instantiating our map object looks like in JavaScript. And you see that we have the map centered on Valencia. And we also want to note the style file, and it's the same file that we have downloaded from the map styler, a JSON. The last few lines are key here as we enable the visibility in JavaScript of the traffic flow and the traffic incidents, which are two distinct and related traffic views. One showing accidents happening independently as incidents on the map, and one showing direction and traffic slowdowns as the colored road segments from the last slide. And then this is what our traffic enabled map should actually look like at a basic level with a basic style. And we would be ready to move forward at this part as we walk through the basic setup of the project. And so for this part, I'll actually hand it off to Jose to explain how we add geocoding and reverse geocoding to the project.
I just wanted to tell that we did choose, we had to select a city in advance. So we decided what city in Europe we can select. Well, let's go on one with a little small streets, I guess. Valencia just sounds as good as any, right? So in geocoding, okay, once we already have the map set up without the site style that we downloaded from the map styler, for example, the first API of the SDK, in this case, we're going to use the SDK for web, that means it's in JavaScript. We're going to use the geocoding API. So imagine we are receiving an order by telephone for the first time. So the first initial information that we have is an address. With the geocoding API, we can get this address, and from the address, we get the location, which is what we want. We want to get the lat and long, the coordinates, of course. It's nice that we have some kind of flexibility, more flexibility with the geocoding API, because not only we can pass a query, for example, to type the address, but also we can send structured data if needed. Next. Yeah, so for our demo, we're going to pass the bounding box of the current visible map in order to get addresses that are more related to the map itself that we have in front of us. And once we have a good set of coordinates, let's go next. Yeah. Once we get a good set of coordinates, then we can add them to an array of destinations. In this case, these are our deliveries. And then we add a marker to the map. That means to add a location and display on the map. So next, and this is how it's supposed to look like. In this case, we didn't start with Valencia. I think we moved initially to Berlin, and we type, for example, I think it was Kochstrasse. And we got an address, we type, we add the location, and using the geocoding API, you get the location of the address, for example. We have also another address there, yeah. Okay, next, we go to the next. What do we have here? Okay, but for our demo, and to make it easier to simulate backend calls, because not, let's be honest, officially or in reality, you will always have the addresses, for example, coming from your backend. So we have to simulate somehow. So once deliveries come from another database, for example, we are going to simulate them like from taking them from the map itself, like clicking on the map. So if we click on the map, we get our location on the map, and using the other API, this is reverse geocoding. Then next, using the reverse geocoding API, we're gonna get the address representing this location. And once we get the address, that's it. It's the same situation. We get the address, we create the marker, and we add it to the map. Yeah. Okay, let's go to the next one. So from the geocoding process, for the reverse geocoding process, we are assuming. Oh, you're going too fast, Olivia.
Oh, my back one.
Yeah, one more.
Oh,
behind.
I'm advancing.
Yeah,
instead. My bad. Okay.
That one. So from the reverse geocoding process, we are assuming that we get at least one good result, which bring them then in an array. The API will return usually an array of possible locations related to the latent one that we just passed. And then we take the first element, just focus for this demo, and that's our address. We add it to the delivery list immediately. The object that I'm going to add to my delivery list in this example is a JSON object. We have the name. In this case, it's just the consecutive number of the delivery location, delivery 1, delivery 2, delivery 3. In this case, we add the coordinate itself, and we're going to also have a reference of the marker that we created. I added the marker as a reference because maybe later I wanted to modify the pop-up or have more information updated on the market itself. Depends on the information that we can provide in the front end, for example. Good. Next. Next. Yeah. And when we have the destinations, go ahead, Olivia.
Sorry about that. So now that Jose's explained how we use reverse geocoding to find addresses and push deliveries, I'll talk about how we take those destinations and we plot the optimal routes for them. And first, it's best to understand the concept behind routing, which is why we have this very entertaining traveling salesman slide. TSP, or traveling salesman, is a mathematical concept that has a lot of really long-winded explanations that you may have heard before. But all you really need to know is that there's no one and done solution to find the shortest path between 2 points. And the famous question is, of course, given a list of locations and the distances between each pair of locations, what's the shortest possible route that visits each of them and returns to the origin? I mean, are not necessarily doing origin return all the time, but this kind of gives a quick summary of what TSP is if you haven't encountered it before, but this is our basis for how we encounter routing. But then TSP is only solvable by checking all the possible paths from A to B or B to C, et cetera, at very high speed and routes. But here's the thing, like routes aren't paths, because when we think of path, we want to think of a straight line from A to B, because normally when you encounter in math, they're just on a simple plane. In like over here on this graph, it's just a straight line. But here we obviously have to tweak it because our paths need to actually fall along routes, and they have to fall along real roads, which is different than calculating a distance as a straight interrupted line. This gives us a lot of other information to work with, like corners, traffics, stops, and twists and turns, all of which really affect the real distance. So even though you can take the literal distance between A to B, like diagonally across a city, that's not going to be the same as the distance that falls along the road. And so we adjust this in our food delivery to allow for multiple stops, which we'll talk about in a second. But obviously we want to make a lot of other provisions for stops along the way or traffic at different times, which maybe alters the time between two points, maybe along a shorter section of road and things like that, which we'll get into the closer we get to the actual demo itself. What we did here, though, is we use matrix routing to build our multi-stop routing for this project. We specifically alter it to use nearest neighbor, which is a specific type of shortest path algorithm. And this is a really good explanation that we found when we've worked with this topic before. If you didn't know already, Jose and I stream development topics and maps on Twitch. And so we've talked about matrix routing before using nearest neighbor. And so this is basically a quick summary of the algorithm going from the starting point, getting the remaining available points based on distance and choosing the closest and going from there. So rather than going from point A to point B, then back to point A to point C using one route at a time, we obviously want to conserve time in FueL by making multiple stops along a route, like a delivery route. And we do this, of course, sorting by time and sorting by distance in our demo, because as you can see, it's not necessarily all the same route all the time. Sometimes it ends up being equal, but as you'll come to see, there are a couple different factors which play into it. So what we're doing is we're going to use it to chain link our destinations into stops. We want to answer two main things. What is the cost of traveling to different destinations, one after the other, using our nearest neighbor algorithm? And then second, what is the most optimal route, one created with faster speed or shorter distance in mind? And keeping in mind that when we create routes happening in the future, we use historical traffic information, which will tell us the average congestion normal for different road segments given at a specific time in the future. So as we're accounting for speed and distance, we're also accounting for traffic within the routes. And if we're planning a route to leave immediately, we have access to live traffic, but at the same time, if we're planning a route in the future, such as future delivery stops or different scheduled deliveries, we'd be using that historic info. And for every loop, we calculate a cost in the optimization process from our current location to the rest of the destinations on the list. So once we have the order of the deliveries, we construct the route, and we have the cost in an object, which has already given us the correct order of waypoints. We fetch the directions. We also want to get the route summary. We do this accounting for distance, aka the length in meters, and time, aka the travel in seconds. And we already account for traffic and different factors when calculating the route itself, as I mentioned. And we also want to get directions and send them to the delivery truck maybe. And of course, we want to display the distance versus time summaries on our screen so the user can see them in the demo itself. This will help us illustrate the different routes and have them show up differently, because as you'll see, we'll show the difference in routing with a preference of the shortest distance versus the shortest travel time, because they're not always the same. This important principle, yeah, exactly. It's an important principle in building a mobility application, as multiple stops and outside factors have a lot of outside effect on what many map users just know as the one and done best route, which is what we'll try to showcase coming up. And then this is where we'll go and shift over to our demo. So I'm gonna go ahead and close my screen share, or actually, Jose, just go ahead, I think, share your screen and we'll take over,
yes.
I think.
Let me see. I got the screen share. I will stop your screen share and I will share this desktop.
Okay. Cool.
Okay,
here we are.
See my can you see my desktop?
Yep.
Okay, as Olivia mentioned, yeah, we're going to try to optimize a multi-stop route, like multiple deliveries, based on speed or on distance. So, of course, when we create routes using the routing API, we have the option, several options to depending on what type of route we want to create. And not only create the fastest route is usually the default option, but you can also get the shortest route if you are not interested in having traffic information, for example, in the calculation. First, I want to let you know about the. Okay, I'm gonna put my screens in this side, so you will see that I'm moving around my eyes. I want to let you know that the source code of this is in GitHub, in a GitHub repository that you will have access. Maybe I should paste it right now in the chat.
Put it in the chat.
Yeah, let me just double click here. Let me just check here. This is. You can see
and that's
here.
the GitHub.
This is the GitHub repo. Yeah. Yeah. Demo. All right.
So that way you should have access to the code behind what we're seeing here.
Correct. Okay, so in this demo, we selected a random city, as I mentioned before. Valencia is also very good because it has a lot of small streets, and I wanted to make it a little bit challenging for the demo. You can notice that we have some traffic layers in our map, and these are visible because we selected a style using the map styler that first is a lighter version of the default map, and I wanted to see the traffic flow. So you can see how the actually let me tell you, this is real. This is real time right now, of course. Let's go on traffic here. And this roundabout, yeah. And we have selected a location. the location of our distribution van or the origin of all of our routes. I think it reads Carrera de Játiva, number 16. Yeah, and we are going to populate the delivery list. I mean, the destinations in this area in the left side of the screen. And once we have an optimal route, we will display the instructions and guidance on the right panel that I have here. You can also see on top of the map, we have the field for our geocoding operation. And since we haven't decided in advance before doing the demo, I remember, if we wanted to do it for speed or for distance, I am calculating both of them at the same time, and we will display the results below under the map in the center panel.
And that way the routes should also layer on top of each other, or wherever they overlap, we should see
it will probably
colors,
overlap,
right?
or sometimes. And since we are gonna be quite closer, it's possible that actually both routes could be the same.
A lot of times they are the same, but sometimes if we get lucky, you can see the different colors obviously going on the different routes, and that's what will show us.
Yeah. So okay, let's see. I'm gonna put an address here. I have recorded an address before. It was close to the beach. It was La Calle.
Because we always want to go to the beach.
Lately, yes. Calle Mar de Creta. And as I mentioned before in our explanation, we're going to use the API. Oh, there it is. Calle Mar de Creta. And
they're very different routes, as it turns out.
Well, what I was doing is we are optimizing, of course, in this case, we are not optimizing anything because we already have only one destination. There's no optimization here. So we're going to create a route from the origin, which is our little van is here, and to our final destination. And the red layer showed by speed. That means we're going to go to the fastest route. And the blue one is, of course, the shortest route. It came later. You will see that the layers are not executed like immediately at the same time. It's because obviously there is a process that happens in the background, and one has to be happening first at the other one. It will be possible to have multiple destinations when the comparisons between the shortest and fastest, and we have optimized the solution. Let me see. I have another address here. Right, I like it because it worked very nice before. This Calle de Hero. Let me see. Calle. Let me see. Zooming. You know what I'm zooming out, right? Because we are geocoding on the bounding box of the map. Calle Hero Romeo. I think it was number 10. Let me see if I find it. There it is.
Oh, that's our second stop.
That's our second stop. So in this case, now we are trying to optimize because we have more than one destination. And in this case, both the route that the algorithm detected, you will see in the code, is first from the headquarters, HQ, you go to destination number 2, and after that, go to destination number 1. You will see that the route in the fastest route is 49 minutes, 16 seconds, and it will take 20 kilometers to go. The shortest route is 16, which is in blue, and it will take around a little bit longer, 55 minutes. So, but this is basic. So let's do some more. Let's do some more. Let's see, I got an address. Will be possible. I remember that I mentioned about the reverse geocoding. In the reverse geocoding, we just click on the map and we get an address, and it will be reconstructed the route as well. Let me see if let's take a look. Let's go to this address here, this building. So this building, it goes to Avenida Las Tres Cruces in Valencia. That's why I have the address here. Maybe you can see. Can you see here the address after the reverse geocoding happened? And we have already a calculated solution. And again, it can happen. Could be exactly the same route. Please go to destination number 2, then number 3, number 1 then, and you will see the difference between the two of them.
Yeah, and in this case, it goes to all the destinations in the same order. but it uses a different route to get there.
Correct. Now, oh, I forgot. After creating the correct order, we have created a new route, and we can get the guidance instructions. We have, for example, the fastest route in here with these instructions. You can send it to your driver, for example. You can send a copy of your map, and maybe you can convert this into a format that is compatible with your navigation device, especially if you have a PND, a TomTom navigation device. You can use it in GPX format, or you can use a shortest route if you're not caring about destinations, having traffic information. Now, I want to let you know that whenever we create a route here, it says here, we are going to go to destination number 2 first. And I want you to look that when you go to destination number 2, the first time it takes, let's say it takes around 10 minutes or 15 minutes to get to the first waypoint. Now, when the driver arrives to the destination number 2, which is here, 10 minutes later, if we start from now, which will be right now, will be 6:02 p.m., and it starts to continue in the route to the next one, the whole world's changed. You have to notice that all these route calculations have traffic information. It's based on traffic information that is live traffic information when you start. But the moment you already arrive, let me see if I can move this marker. Can you move? Oh yeah. Let's say the driver already is driving here and arrived already to destination number 2. 10 minutes later, the whole thing is changed. You have to because then we have to recalculate, in theory, a new route in the future. And that is possible because we can use historical traffic information. It is this important thing why having here, what I'm trying to say is that here you can see the power of ETAs, the estimated time of arrival, by using the TomTom Maps APIs, creating very accurate routes that are planned in the future with historical traffic information. Remember that this traffic information, when it's real time, is updated every single minute. So once you get this in the future, based on traffic information that happens already historical to calculate a most accurate route, then you can say, okay, now I can go with to this destination following this fastest route. I think it's over here. Let's follow the red line. Follow the red route. And then when we arrive, let's say 45 minutes later or 30 minutes later, we have, in theory, we have to recalculate that again. So this is one optimization that it would be nice to have. Yeah, we can have that in the API. So let me see if I can do something different here. I'm gonna clear the deliveries right again, reset everything. Now I have only show you what small routes. Let's see if I can do like really longer routes. That is those here. I have one nice optimization that you can add if you have access now to the source code in GitHub. I'm planning to add is that I have all this operation happening one after the other, and I'm not using the batch operations. That means it will, since I'm not using batch operations, I have to put a little bit of delay between every call, and that's why you see a little bit of delay of recalculating, because I'm doing like around 1 second per destination. So as you can see,
there's a limit on the queries per second, right?
Yeah, I didn't want for this demo go over my query per second limit, and that's why I wanted to pause the calls every second, for example. Yeah, that's why it's good to use the batch APIs to handle more than one operation at the same time. Okay, this is mostly what I wanted to show you today. I think Dozana can take over now. Where is should I stop the sharing screen? Where's the other? Stop share. You can continue with the last slide. I think you have some QR codes.
Yeah. So Olivia, do you have the?
Yeah, I'll go ahead and reshare the screen. Okay, good.
We do have some time, so okay.
So these are the QR codes.
Okay. Yeah. So thanks everyone. I mean, it was pretty fast. I do think there's like a lot of APIs you can use, and you can see, hopefully you took some away from this presentation. But if you want to play more with some things that we showed you today, we do have the GitHub demo, or we have it on GitHub right now. So you can scan the QR code to get to there. Also on our developer portal, there's another tutorial on pizza delivery that's kind of similar and walks you step by step with our SDK. And you can also access that at developer.tomtom.com through Web SDK, and then you can click on the pizza tutorial, and there's also a QR code there too to access it quickly. And we've also provided a coupon code for you, Food Delivery 2020. If you'd like to get started right away, it's 10,000 free credits so that you can start at least playing with some of the code without having to pay much. But yeah, that's pretty much it for us today. We're a bit early, so I don't know if we have access to also questions.
We do have questions
out there.
I can see some questions.
We do. Let's
Yes.
see.
Oh, we do.
Can you see
Okay.
questions? Okay.
Oh, I'm back for the question. I bring the questions.
Hello, Stefan.
Hi. Okay. So the demo link you posted is not a question, but it has upvotes. So I think people will actually go to GitHub, and people don't forget to put a star on the. Yeah.
That'd be awesome. Olivia, do you mind going back so that it can be
let's go back
shown?
one.
Yeah.
Perfect. Yeah.
Yeah.
So this is the QR code for the GitHub if you don't see it posted
Perfect.
in the questions.
So the next question is, in case we'd like to calculate the route for a delivery in the future, for example, Sunday, are traffic info in some manner predicted?
So that uses the historical traffic information that we know about the past congestion. And so it's basically making an assumed prediction based on how much congestion is usually present in a given area. So say if you're routing along, this street, it'll take the information based on the congestion that's normally at that time on that day on that street.
Yeah, I have to say that the traffic information we've been collecting for more than 10 years, more than a decade, I think, right? Yeah.
Yeah.
And that only gives us the advantage that to know that in a certain, in every road segment that we analyze traffic, we know exactly what is the real flow. So we don't take in consideration that the speed limit is 30 kilometers per hour here, so we just calculate this. We actually take the real value. We store that, and we have that in creating what's the name? Profiles, right? Speed profiles.
Our speed profile.
Yes,
so yeah,
profiles.
Yeah.
If you guys are interested in the technology, I would recommend going to tomtom.com. So not our developer portal, but tomtom.com, and we kind of talk about how our traffic technology works there. And this is where I kind of like brag a little bit, where TomTom is famous for this specific piece of technology, especially. And it's not so simple. It's just historical traffic. Our speed profiles actually is also a type of algorithm that weeds out some of the outliers, for example, some aggressive drivers versus very conservative drivers. And it's actually quite intricate and complex as well. But what's cool is that all of that is packaged into our routing API. So, yeah.
So yes, the answer is yes. It will be taken in consideration, and it's actually the option by default. Yeah, by default, when you create a route, it's always taking in consideration traffic, unless you say no. Then it's a parameter. You say no, it's fine. That's what.
Okay. So, next question is somehow similar to that. Will the system learn back from the shortcuts local drivers take?
Well, and let me see if I can understand. So questions, it would be, when you say system, you mean your application, our application. Well,
Yes,
in this
I think
case,
the routing
the
thing-
routing, well, the routing just guiding you is not taking, we are not, in this case, we are not receiving your location and storing it somewhere, for example. We're just delivering you a, or creating a route for you based on the parameters that you sent, that you guys sent. So the answer to the question would be, it would be yes and no. Yes, if you actually store it. You can get a route and you can store it temporarily, yeah? Then you can say, okay, I want to save it for later, for example. Is it that? I think it's possible, of course. You have the route itself. Dosana?
Yeah, so actually, I think, so yeah, to Jose's point, if you are talking about your own routes, your own drivers, then yeah, it would have to be stored, and you can store it and then also analyze it yourself as well. If you're talking about just in general, like as in general, are these streets that individuals take, kind of like the shortcuts and whatnot? You can definitely customize the routing to avoid certain road classes or toll roads, for example. But also the way our algorithm works is, like I said, the speed profiles, and it takes into account like also a mixture of multiple things, right? It's also the fastest, what's the most reliable ETA, and also what are frequently traveled routes. So it's kind of a mishmash of all that information, kind of going back to what I was saying about like there's all these different types of algorithms that can be. So that's our little secret sauce, and the ingredients that we use to choose the best route. A really good example I can give is recently a customer came to us and was like, oh, hey, how come you're taking us on this really long route, but your competitors show that you can take, this much shorter one? And so when we investigated, we actually, took a deep look at it and realized, oh, well, the reason why our algorithm chose a different route was because there was no one taking that path based off of our traffic data. And when we really looked into it, it looked like that route was completely closed off to begin with. So it's not even an option to take it. So the data that we do have has shown like, okay, these are the type of routes that you can take. So it's a bit of a long answer, but I hope that kind of helps to explain like, you can use our information. So, some of the roads that you can take, you can also tailor it if you want, like the small local routes, like small local roads. But then also, if you want to base it off your driver's knowledge and whatnot, you can also save those and analyze it later.
Okay. So next question is something which might help with these company profiles. Could we include data like how much fuel his or her tank has, brackets, gas or electric power, and include that too?
Yeah, you can integrate the EV routing. Jose's really interested in EV routing, so I can tell you're perking up. I can let you explain,
No, it's okay. It's okay. Yeah, of course. The routing API is a very rich and complex API.
Yeah.
You not only can have the options to pass how much fuel you have, but you can pass, this is how much fuel I have, and this is how much fuel I consume. Right, and it can calculate. Okay, so based on this information, you need to go through these directions, or you can only reach up to this destination. So you better charge, because we can calculate the reachable range, especially for that. Also,
you can use the reachable range with the electric, and you can also use it with the combustion engine. So you can toggle it even. So you can change back and forth depending on your starting fuel level or starting battery and things like that. And if you want to get more into it, you can even include charging stations on the route and things like that.
Cool. So, it's a question from one of my cost-sensitive friends. Is there a free limit of cars?
Free limit as in... Well, we do have a when you get the free API key, you start working in a freemium mode, right? That means you have 2,500 free transactions per day that are deployed every day.
Yeah.
And there is no limited amount of code you can do. You just get I think you get an error when you go over the limit, right now. But you can.
But should be enough to get your app up and running.
Oh yeah,
I think
2,500 transactions is usually more than enough to start any prototype or even startup. I already have startups using the freemium mode for months, and before they start, okay, we're done. We're gonna start trying this thing.
And you can use the code as well that we put here. You can have even more calls, so you'll have plenty.
Yeah, this will
and
give you 10,000.
Already a product on GitHub. We just need to replace the pizza with whatever.
With a burrito or
your imagination is limited.
Okay. So next question is one from Sebastian. Do you offer real-time traffic information in small cities or trust third-party providers? That means a street gets closed in a town. Will I get an alternative route?
Yeah, so our traffic APIs do have both the actual traffic flow, but also the incidents, so that you can avoid those incidents. And it's built into routing so that it'll avoid them. In terms of availability in small towns, we do on our developer portal, you'll be able to see the availability in which countries they're at. So that would be able to be helpful. But if you need a specific area and you still don't have the answers after you look at that, then yeah, you can feel free to comment on our community board there, and we're happy to research it for you too.
Okay.
And the live traffic, if it's available, will be it's minute-to-minute updates.
Okay. So the next question, anonymous question. Ooh. Any hypothesis to adjust the route dynamically while the driver is reaching the destination through regression?
It is possible, of course, that while the driver is literally on the road, something happens on the road. So our application, in this case, in the demo, you can recalculate the whole operation from the location that we are right now, of course, and it will give you a new set of rules, a new set of destinations, or a way to go to complete the route. Remember that, yeah, as Olivia mentioned, traffic is changing every second in the city, and we updated it every minute for the API. So that means the route in principle can change every single minute. Yeah. I know that some other companies uses the default for 10 minutes. That every 10 minutes, usually delivery system, after 10 minutes, let's recalculate just to check. And you can see, okay, there's no change or continue. Yeah. Hypothetically, yes, this is possible.
Okay. Yeah. Then another question from Sebastian. Do you also offer routing considering passengers pooling multiple passengers on demand taxi case? This is what he said. Interesting.
We do have a demo for that, right?
We actually do have a demo. So in that same web SDK place, right next to the pizza tutorial is a
Let me find it. I will put the link
tutorial.
Yeah.
So you can check that out. But in terms of number of passengers, I don't know. I don't know.
It's taxi specific, right? Not necessarily carpool specific, I think.
The room.
Yeah.
Yeah.
Taxi specific. Let me see it. Taxi. Like for example, if we have several, that we have to pick up several people, something like that.
Yeah, I think it's either people or
we have several autos.
So you have maybe you also want to pick up several pieces of mail from different places and deliver at the same time.
Sure. Yeah.
Effectively, you could use similar portions of the same demo, because the at least in our demo is not necessarily focused on like delivering food, and you could be picking up people at the same stops, right? So it has a lot of the same principles.
Okay.
Cool.
So thank you for posting the link.
Yeah, I did. I did post the link for the next sample about the taxi cars example.
Henrik says, "Awesome talk. Thanks a lot."
Thank you.
Thank you, Henrik.
Thank you. Yeah, you're great, Henrik.
So awesome. Wow, so many questions.
Oh,
that's great.
Yeah.
Yeah.
We still have some time too.
Yeah, and now we still have time. Gary, what can we do? Oh. Gary wants to use a delivery service.
It's very easy actually. You once you download from the GitHub demo, it's a Node.js application in JavaScript. Yeah. So it's quite. We don't in this demo I didn't use any frameworks, no heavy frameworks. So we don't not even Angular or jQuery. It's very easy. Try to keep it pure JavaScript, so it's easy to compile everywhere.
Okay.
I mean, run everywhere.
I mean, as a market expert, I will say that there's still a lot of room for people to enter into this market and kind of give these companies a run for their money. So definitely it's kind of cool. And I've also seen where it's like this is running in the back end, all these APIs, right? The matching and optimization. But in the front end, it's actually in WhatsApp. I think there's an article about that, I think Captain, and in certain areas like in the Middle East where Wi-Fi or connection's not so great, and so that you're able to actually request through WhatsApp, and in the back end they're doing all the matching and routing with whatnot, and then and then it'll come. So kind of like a poor man's, that one's for a ride hailing, but a poor man's food delivery. I'm sure you guys can build too.
Yeah,
kind of cool.
So, people of Vienna who are in lockdown, like the rest of Austria, this is the blueprint. Now you just need to create all these services we need right now. We don't have, so we don't have to cry. Okay. So now I ordered a lot of people to create all these apps. Okay. So thank you, Tosana, Olivia, and Jose. It was very nice talking to you, listening to you. And I think it was also very cool for all the people watching to see like how easy it actually is to get a working prototype with technology in the backend, which is strong and where you can rely on. Okay, so have a nice, I think, evening, day.
Yes, evening.
Jose is in the
Thank you.
evening.
Thank you for having us.
Yes, thanks so much, everyone.
Thank you for having us.
Thank you for
wherever you're
coming.
checking in. Thanks to everyone.
Thank you. Bye.
Bye.
Thank
Bye.
you.
So, Gary, I think you put on the loop, and then we have the next event on this day. I wanted to say goodbye because Vessi is already gone home. So, day 3 of the mobility days are over, but don't fear, the Live Week is coming up, 30th of November to 4th of December, a full week of developer candy store. Wow, awesomeness. So Europe is in lockdown, and this means I only have one message besides please register for the 3rd edition of the Live Week. It's stay healthy, use a mask, wash your hands, you know that, and take care of people who cannot take care of stuff, like the elderly lady living next door to you might need a helping hand when going shopping, and I'm sure you already did that. Yeah. So that being said, see you in the Live Week, or also maybe next week to the Laravel talk with Christoph. And in the meantime, if you missed any of the days, they are on YouTube. And if you have any suggestions of people you want to see, ask them to write to us or write you to us and introduce us. You will find plenty of contact possibilities on the webpage. And have a nice evening. Bye-bye. Are you still here? Yeah, I believe so. It's really the end of the mobility days. You know, we all have to pack the things and get home before curfew. Because otherwise we will have to stay in the office and work through the night. Gary, do we have some more talks for the night?
No, we're done for today.
Okay, so you will really have to wait until next week or until the beginning of December. And Thomas, please stop texting to us. Thank you.
Take care, stay safe, see you soon.
Bye-bye.